In this lesson, we're looking at MAT2615, calculus in high dimensions, and also called multivariable calculus. We'll spend time solving a wide range of problems from the most basic to advanced. Right, we're looking at this particular question, and we need to calculate the equation for the plane containing the lines L1 and L2, where L1 is given by the parametric equation, the first one, and L2, the second one. And we reiterate the fact that to calculate the normal to the plane, note that both vectors 1, 1, and 1, and 1 minus 1 and 0 are parallel to it. So they are parallel to the plane because the lines are contained in the plane. Okay, so a normal vector is given by the following. And obviously, a normal vector, the word normal means perpendicular. Okay. And we want to find the normal, and we find that one. So we take the vectors here because every line passes through a point and is parallel to the vector, passes through a point parallel to the vector. So we have this one here. And we have this one here. And we have I, J, K. Okay, yeah, 1, 1, 1, 1 minus 1, 0. Let us compute this. Okay, and obviously as we compute, we use coefficient expansion. We remind each other, plus, minus, plus. Those are associated signs for computing our normal. Okay, so we'd have therefore the unit vector I, and therefore we multiply, block this column in which I appears and the row, then we're left with 1, 1, minus 1, 0. 1 by 0. Minus 1 by 1. Okay. Yeah, we block this and that. 1 by 0. 1 by 1. We block this and that. 1 by minus 1. Okay, 1 by minus 1. And then you have 1 by 1. So you minus 1 by 1. Right, this is our hope that everything is okay here. Now, if you continue here, what do we have? Well, 1 by 0, which is 0. And this is going to be a plus, because this is negative by negative, is going to be a plus 1. And then obviously you multiply with the I, it gives us the unit vector I. 1 by 0 is a 0. This is minus 1. Minus 1 times the j gives us plus j. Minus 1, minus 1. It's a minus 2, and this gives us minus 2 times the unit vector k. Okay, I was making a quick remark, which I will make again here. Z, y, and x, and yeah, and then obviously the unit vectors are I is the unit vector on the x, and j is here on the y, and this one is our unit vector k. Right, and obviously our usual notation, because this is 1, 0, 0 for I, and therefore the j unit vector is 0, 1, 0, and the k unit vector is 0, 0, 1, which introduces 1 in the third component, because this is x, y, and z, and therefore the z is the third component of the order triple. Now, okay, this is what we get, and this, in other words, if we find this is called the vector product. Right, so the vector cross product, because they are vector products that we learn. And now there's something called the dot product, and this is called the cross product. So yeah, this vector that we get, because if you find a vector cross product of two vectors, you get a vector as well. So this is 1 minus 2. Okay, so yeah, that's what we have. So we can write it either like this or that way. Okay, now we have found therefore, so this one here is our normal, and in this module we write it like this. And we write it as the n with the by the bottom, and this is a normal to the plane. Why? How do we know? Because we took two vectors that we said are parallel to the plane, and therefore if you find the vectors that are parallel to the plane and you cross them, what you get a vector that is perpendicular to the plane, and that is how we find normals to the plane. Okay, now we have that. Let's continue to solve this problem. Let's continue to solve this problem. Then the point, right, the point. There's a point, and the point 1, 0, minus 1 being, right. Okay, now we're taking this point. We're choosing this point, but yeah, you can choose any point. But we are making a remark about this point 1, 0, and minus 1. So the point, because these are, you can use either this point or that. Right, the point 1, 0, and minus 1 being in the line. Right, being in the line L1. In the line L1 is in the plane, in the plane 2. Okay. Obviously, we are noting that this point is also in the plane. How do we know? Because the examiner told us that we need to find the equation of a plane, and this plane whose equation we need to find contains the lines, and if it contains the lines, it contains also, in other words, the plane contains the points on the lines, on both lines. Okay, right. So the point, this one being in the line, right, so yeah, because this point is in the line, is in the plane too, because the line is contained by the plane. So the equation. Right, so the equation of the plane. Right, so the equation of the plane is given by. Right, so the equation of the plane is given by. There's a formula we use in this module. And what is the formula we use? We use the formula as follows. Right, we use the formula x dot normal equals point dot normal. Okay, this is the formula we use to find the equation of a plane. What is x? Vector x is an arbitrary vector with x, y, and z components. And then we have the normal we have already got. What is the normal that we got? Okay, it is 1, 1, and minus 2. That is the normal. So we take it. So we have 1, 1, minus 2. That is the normal. And then we took 1 point. You can take any point, either this or that, because they are points on the plane. They both must work and they must give us the same answer. So we're going to take just the first one, make that choice. And then now we find this is the dot product of the vectors. So now the vector dot product, we put the normal, and we got the normal so this normal is the same always, 1, 1, minus 2. So that's what we plug in here. Okay, what is the dot product by law, and how does the dot product work? Okay, we do component-wise multiplication. So x by 1 is x, y by 1 it's y, z by minus 2 is minus 2z. Okay, so you have 1 by 1, it's a 1, 0 by 1, it's a naught, minus 1 by minus 2, a big 2. Giving us x plus y minus 2z, and the result is 3. And it's everything we ever wanted, because this is the equation of the plane. And this is the answer to the question. Okay, now another student is going to come and say, hang on, what about if I choose different points? You know, the answer will be the same. It must be the same because this is all mathematics. The principles themselves in mathematics must hold true. Okay, they must hold true because I'm going to do it in green color because another student, I'm going to just squeeze it here. If you have x and this is the formula for finding the equation of a normal, or rather the equation of a plane. Okay, so you have x, y, z. For the x, dot the normal. Okay, the normal is the same one. But it takes, yeah, because we just use these two vectors there to find the equation of a normal, but yeah, you could use more. Okay, yeah, you could use other methods, but yeah, the point P, yeah, I was saying we use this point because we used here the 0.10 minus 1. Let's test mathematics and its capacity to hold true if somebody uses a different point. Okay, and then now we're using the 0.210 dot to the normal 1 minus 2. This one, x by y minus 2z. 2 by 1 is a 2 plus 1. Okay, that's 2 by 1, 2. 1 by 1, 1. 0 by minus 2 is a minus 0. And this gives us x plus y minus 2z equals 3. Okay, that's what we got. We got the same answer using this point and also got the same answer using that point. So, and this is very versatile. I can give another task to you and say to any student, if you want to test, obviously, these answers, you'll find the same equation of a plane. Even if you take this point and take that point, 2 points can yield a vector. Okay, if you take these 2 points, point 1, point 2, and you subtract them. So in other words, you can say point 1 is, okay, we're moving on to the next question. I'm just discussing planes and lines. And now you have point 2, for example, which is 2, 1, 0. Okay, points can be given like this. So that in the end, then you can find point 1, point 2, and this is going to produce a vector, right? So, and this is 2, 1, 0 minus 1, 0 minus 1. And in the end, then we have 2 minus 1, which is 1. And then 1 minus 0, which is 1. And then 1, put a minus here. That is 0 minus minus 1, which is 1. So yeah, you're going to get another, hey, this is awesome stuff. Look at what this, sorry, this is giving us a vector. In particular, it's giving us the same vector there. So you're able to see that if you take these 2 points, you really can be able to get a vector that is formed by, you took 2 points on the plane, and if you subtract 2 points on the plane, what you get is a vector, and vectors can be used to find the normal. So you could use, but yeah, it produces the same vector. So it means that you can use this one and this one to find the equation of a normal. I was saying then for the normal, you can use different vectors that you can form using points, etc. And we use the 2 points, but yeah, it produces a vector that we already have. But we've already used the vector 1, 1, and 1, and this one to calculate the normal and etc. And we're able to find the equation of a plane. And the equation of a plane is x plus y minus 2z is equal to 3. How do you know this equation is correct? Because now, you see, you can get the equation of a plane in the exam. How do you know it's correct? If it is correct, this equation of a plane, it must be made true by, sort of satisfied by points on the plane. And now we can take a point on the plane and it must make it true. It must make this very, very true. Let's take 1 point. So we're going to do a quick check. Okay, we're finishing this problem and then we're moving on to the next one. Okay, if you take a point like this one or that one, okay, let's just take the first one. 1, 0, minus 1, and you substitute it into this. So it's going to become x plus y minus twice z. And this is like, okay, the point has x, y, and z. It's an ordered triple so that x is 1, the y is 0, minus 2 times z is minus 1, and the result is minus 2 times minus 1. What then are we able to achieve here? This is 1 plus 2 because negative times negative is positive, and the result is 3. So indeed, we can say that this equation of the plane is correct because if you put the coordinates of a point on the plane, you get that the left is equal to the right. Okay, you plug in the x, y, and the z, and you get 3. And the 3 is the answer. It is the answer to this problem. Okay, next question. Okay, now dealing with planes and lines is also something very, very exciting, but also we've learned before in the previous example that we've gone through, we've learned how to find the equation of a plane, and we shall spend time also learning how to find equations of lines. Okay, so we continue as follows. given the two planes x minus y plus 2z minus 1 equals 0, and 3x plus 2y minus 6z plus 4 equals 0, find a parametric equation for the intersection. So we continue. Right, so we need to find a parametric equation for the intersection. Given the plane these and that with those two planes, how do you therefore find a parametric equation for the intersection? Because these planes potentially intersect. Okay, we have one plane that is coming this way, and then suddenly there's another plane that is such that it is this way, etc. And now it actually sort of intersects at a point. And if this intersects and maybe they are perpendicular to each other, that kind of a situation, right? So what then you can have is a situation where these two planes obviously intersect. But given two planes, you can have planes that are parallel to each other. Here is one plane and here's another plane, and these two planes can sort of be parallel to each other. Okay, so, or they can be planes that intersect at some distance. Okay, because yeah, the planes themselves can either intersect or be intersecting planes or parallel planes. Okay, so that's something that we can obviously note. Okay, let's look at this. Given these two planes, what then the examiner wants? The examiner is saying find a parametric equation for the intersection. These planes will intersect if you sketch them, and then we need to find the parametric equation for the intersection. Let's do that. So we must write them over each other. Right, so you're gonna have like x minus y plus twice z. And we can equate this to 1. And then we have the other one, 3x. 3x plus 2y plus 4 z. Plus just, okay. I need to write this correctly. Right, obviously we've written this correctly. It is x minus y plus 2z equals 1. Okay, let us write the next one correctly. So this one here. So it's going to be 3x plus twice y minus 6z is minus 4. That is what we have here. So what we have here, therefore, is as follows. 1 minus 1, 2. 3, 2 minus 6, minus 4. Okay, these are the equations of the planes, but yeah, we have put them together into what we call an augmented matrix, and we have written that in the form of an augmented matrix. Augmented matrix. All right, so in this augmented matrix, then we're going to solve this step by step. But now, to find what are we doing here? We're given two equations of planes, and we want to find a parametric equation for the intersection. So yeah, we're intersecting them. So if we're intersecting, if two planes or yeah, two or more planes intersect, we put them in augmented matrix and we row reduce this one using what we call Gauss-Jordan elimination. So we're going to proceed to use what we call the Gauss-Jordan elimination method to find the parametric equation for the intersection. So we proceed as follows. Yeah, we're good. So we're going to start. We can write this one first and the other one, etc. So yeah, we have 1 minus 1, 2, then 1. We have 3, 2, minus 6 together with minus 4 that way. And then we will reduce this one to, because there already a 1 minus 1 to 1. We're going to get a 0 here. So we're going to say, for instance, row 2 minus 3 row 1. Row 2 minus 3 row 1. So now you multiply by minus 3 and you add, you get a 0. You multiply by minus 3, you add, you get a 5. Okay, because you multiply by minus 3, and then you say minus 3 plus that, you have a 0. Multiply by minus 3, then you have 3 plus 2, you get a 5. Multiply by minus 3, you get minus 6 minus 6, which is minus 12. You multiply by minus 3, You have -3, -4, you have a -7. So this is what we have. Okay. And this is awesome news. Awesome news. And then after this, right now, we think about what can be done, and we can therefore be in a position to get the solution to this. And one way to do this right now is to get a 1 here. So, yeah, I want us to use the methods very well. So we can multiply by 1/5 row 2, which is 0, 1 minus 12/5 minus 7/5. And then 1 minus 1 to 1. And then now you have row 1 plus row 2. And then we have 1 plus 0, which is 1. 1 minus 0, rather 1 minus 1. Okay, so we're adding row 1 and row 2. So if you add 1 plus 0, you get a 1, and you add these 2 here, it's 1 minus 1 is a 0. And then now you have this one with this. Okay, so this one you can, 2 is the same as 10 divided by 5. And then if you have 10 minus 12, 10 minus 12, everything out of 5 here, you have -2 out of 5. Okay. And then obviously you are adding row 1 and row 2. That is the operation, the elementary row operation. So we add this and that. Okay. But you want to make this one have the same denominator 5. So you can write this one as 5 out of 5. 5 minus 7 would give us a -2 out of 5. So 0, 1 minus 12 out of 5, which is -7 out of 5. So right, then in the end, what then do we have? Okay, we have this matrix here. This matrix here is said to be in reduced row echelon form. What is the matrix? It is 1, 0 minus 2 out of 5. 1, 0 minus 2 out of 5. Just writing that matrix there. Okay, 1, 0 minus 2 out of 5, minus 2 out of 5. And then you have 0, 1, 0, 1 minus 12 out of 5, together with -7 out of 5. Yeah, it's -7 out of 5, this one. Okay, need to stay wide awake to make sure that our numbers are correct numbers. We need correct numbers. Okay. Now, we recall something, but what do we recall? We recall, therefore, that we started with these equations that examiner gave us, and these are X, Y. These are past exam questions, so yeah, need to just make sure, obviously, you understand them, and they can always surprise you there, okay? Introductory part of this course. So the first equation, the first row is X minus 2, Z out of 5 is equal to -2 out of 5. Okay, X is 2 out of 5, Z, -2 out of 5. -12 out of 5, Z, equals -7 out of 5. Y equals 12 out of 5, Z, -7 out of 5. Okay, okay, yeah, we just have rewritten this one. So it is actually X minus 2 out of 5, Z equals -2 out of 5. Here you have this one is Y because the X has 0 associated with it. And you have that this is the case then. And we then have the following, the -7 out of 5 there. So yeah, so we proceed then to solve this particular problem here. So in the end, then also you have the following. So you set, let's set Z equals T. T a parameter. So what we then do is we set Z equals T, a parameter where T is an element of R. So, and if we do that, we're able to get therefore that x is going to be the same as what? X is going to be the same as 2 out of 5 t minus 2 out of 5. And then we shall have that y is 12 out of 5 t minus 7 out of 5 z equals t. So we have x, y, and z, and we have this. The t is a real number. So an element of the set of real numbers. Okay, so this is actually the correct result. Okay, so and we conclude this one in red color, which can be right, which can be written, which can also, okay, because just another presentation. So which can also be written as, right, it can also be written as the following, right, which can also be written as x, y, z, right. Okay, so we continue. So x, y, z is the following, okay? Right, so it is actually now, and then we can write first the constants. So for x, for instance, you have like minus 2 out of 5. Okay, we continue. We continue. Okay, we continue. All right, yeah. I was saying the x, you take the, for x, the constant is minus 2 out of 5. For y, the constant is minus 7 out of 5. Z has no constant, so it's 0. Plus, and then you have t, and the t is, x is 2 out of 5. And y is 12 out of 5. And z is exactly, okay, yeah, because now if you, t as is t, but you factor out t, and t is an element of R. Okay. So we continue. We continue. All right. So this is the answer. So because you see, given the two planes x minus y plus 2z equals 1, minus 1 equals 0, and the other one, find a parametric equation for the intersection. And now we agree, therefore, and it's very evident from our calculation that these two planes intersect, and this is the equation. What kind of an equation is this? So these planes intersect. So you have one plane that intersects another plane, and if these planes intersect, then what then do we then say? If they intersect at a point, they intersect, and the intersection of these is something we know, because this ordered triple that is equals a point plus t times a vector is a line. So this one is a line in 3 dimensions. So the planes intersect, and what they yield is a line in 3 dimensions. 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 Right. So yes, please.
Is there another method of calculating two intersecting planes besides using the
Matrices?
Gaussian-Jordan?
Yeah, okay. Oh, yeah, okay. Okay, besides using the Gauss-Jordan elimination, is that,
Yes.
yeah, any other method besides using the Gauss-Jordan elimination? Yes, there are methods. We can also do without the Gauss-Jordan elimination, but the Gauss-Jordan elimination provides a very organized way of doing this. a very organized way of doing this. Right. A very organized way. So Gaussian elimination provides a very organized way of doing this. Okay, so yeah, we're good then. We so good. We so good. So okay, I hear you. So we can use other methods like high school. In high school, these are like simultaneous equations. So in high school, simultaneous equations, you don't need to use Gauss-Jordan because in high school, these are like simultaneous equations. So you can use substitution, you know. And the biggest problem in substitution is it's not organized, and you might just end up having superfluous variables, and the whole thing can be messy, can be confusing, and you can have potentially lots of mistakes. So that is something that you obviously will note. And my recommendation would be that the Gauss-Jordan organizes everything, and we can be able to focus on each entry and be able to get correct answers without having to use, because yeah, I mean, these things are there even in grade 10. In grade 10, simultaneous equations are there. That's when they're quite done in a very organized manner at grade 10. Now, if one does them at grade 10, but the grade 10s do not learn these Gauss-Jordan. Yeah, because those equations are in terms of fewer variables as well. Okay. For example, I'll give an example here. Okay, now a grade 10 child can do this question, but they don't know any Gauss-Jordan, and this grade 10 child can just even take the equation like this. I'm just going to demonstrate what grade 10 mathematics can yield here. So you have that. Okay, and then now you have this. You call this one equation 1, and you call this one equation 2. And then now you say equation 1 times minus 3. Okay. Yeah, we do that because we want to eliminate one of the x's, one variable, you know. So we can multiply this one by minus 3, getting minus 3x multiplied by minus 3, you have 3y. This is how the grade 10s can do it because they don't have lots of techniques. And then multiplied by minus 3 here, we have minus 6z. Yeah, multiplied by minus 3 times 2 is minus 6z, plus 3 equals 0. And then this is 3x plus 2y minus 6z plus 4 equals 0. So in the end, then you have the following. So this one then becomes equation 2, and this one you can call it equation like you can call it 1 primed. Equation 1 primed. Okay, I'm just demonstrating what I mean. Yeah, it's not only Gauss-Jordan that can help us do this. So in the end, then now we have this, and we can have 1 primed plus 2. We add them. So we have 3x minus 3x, which is 0. We add them up. And if we add them up, we add the 2y and the 3y, we get a 5y. Okay, the x is gone. And then here you have this one, which is minus 12z plus 7 equals 0. Okay, and this gives us exactly the y. And what then do we have here? What then do we have here? So that in the end then, so we have 5y equals 12z minus 7. You divide by 5. For example, something we got to get 12 out of 5, z minus 7 out of 5. And we got 12 out of 5, minus 7 out of 5. We got that. We got 12 out of 5, 7 out of 5. Okay, yeah. 12 out of 5 minus 7 out of 5. Yeah. Yes. So yeah, we can even do without that. So we can use the school concepts, and then now we got the y there. And after having obtained the y, then we want to get x. So, and obviously z, because there are three unknowns, and now z you can call it t. So yeah, then we have one equation. So we can use like the first equation to get x, because we must be able to get x, y, and z. So now getting x from this equation, so we can say from equation 1 to make it organize a little bit. Okay, you can say from equation. So yes, my point is yes. I mean, you can do without the goes to done. So from equation 1, what do? We have x equals y minus 2z minus 1. Okay, this is exactly y minus 2z minus 1. And then now at this point, because you've already got the y, the z, we can be able to get the x, and we can get the x by using the y. So I'm just showing that we get the same answers here. It is irregardless. So you have this one minus 7 out of 5. So yeah, in the place of y, you put that minus 2z minus 1. So then in the end, then we have the following. So we have x equals, okay, so this one here, for example, you have the z like that. And if you have the z like that, you can be able to get the x, for example, right? You can be able to get the x there. And if you get the x, what will this become? So, for example, we have already got x to be exactly this one here, the 2t out of 5. So you can be able to see here, this one is 12 out of 5 minus 2. So 12 out of 5 minus 2. So in other words, we can just simplify this one on the next slide. So you have this equation, for example, just using quickly 10. So we have 12 out of 5 z. Right. So we have 12 out of 5 z. And then we have minus 7 out of 5. We have minus 2z minus 1. Okay, so yeah, we combine these two. And then now you can make this one out of, do have denominator 5 like this, the z terms. So you can add the z terms. So this one can be minus 10 out of 5. So if you have 12 minus 10, right, 12 minus 10 is a 2 out of 5 z. And this one you can make it 5 out of 5, so that in the end, then you have 5 out of 5. So if you have minus 7 out of 5 minus 5 out of 5, so this will produce actually what we got here, and it is as a matter of fact, so you have minus 7 to 5 and minus 1. So I'm trying to obviously compare with the orange. So we got to make sure that everything is aligned. Otherwise, right. So we have that. So we're expecting our x to actually yield a minus 2 out of 5. So we just obviously need to have that cross-checked, because if we're getting the same answers, it definitely, okay, yeah, here is it, here it is. So this one must be a plus, please. Okay, yeah. If you move this one to the other side, because we from equation 1, move it to the other side. So y is gonna be like plus y minus 2z a plus 1. Yeah, that's what we wanted. So this or couldn't well. So this one is a plus 1. It's a plus 1. So we then getting a plus 1 here. So in the end, then you have this one. So this is 5 out of 5. So 5 minus 7 is minus 2 out of 5. Is minus 2 out of 5. So we continue. All right. So we continue. Right. Okay. All right. So yeah, we're good. In a nutshell, we got using just a grade 10 child, just doing what you call, this is called elimination, because we're eliminating variables. Right. Right. So we have this exactly. Okay. So that in the end, then we have y equals. Right. So y is equal to 12 over 5z. And then we have minus 7 out of 5. Okay, so we have therefore the x, y, and then the z. The z, we call it t. Okay, we got exactly these same answers before. So we continue. We continue. Right, we continue. Okay, yeah. This would mean finishing quickly. Right, using just great 10 tricks and methods. Okay, this method we used here, once again, this one is called the elimination method. Okay, elimination method, and then we eliminated the variable x. There was no x, it was eliminated. And then we went on to use the method of substitution there. Substitution. Right. Why? Because substituted the variables. Okay. So, and at this point, we go to this one, minus 2 to 5, and y is 12 out of 5, t minus 7 out of 5. Z equals t. Z equals t. Okay, yeah, and simultaneously, we can quickly be in a position to summarize this as follows and say x, y, z. And now we have the x, which is minus 2 to 5, the y, minus 7 to 5, and the z now, okay. Remember, we're dealing with the constants, minus 2 to 5, minus 7 to 5. Obviously, we realize that the z does not have a constant term. It only has the parameter t. If we pull out t here, which is 2 out of 5, and then it is 12 out of 5, and this is 1, and this is multiplied by t. Right, it is multiplied by t in the, okay, yeah, it's multiplied by t. We can see the t there. And if this t is multiplied by this t, it's a parameter. And we are able to see and understand that at this point, what do we have? What do we have? Right, this is actually exactly the answer we got using the other method. So yeah, this confirms you can use other methods. So elimination is one of them. Gauss Jordan is underpinned by elimination, but it just uses matrices. Elimination is first learned in high school grade 10, but Gauss Jordan just put everything in matrices, and it's not a a new method, but everything is organized in matrices, and which makes it easier to operate. Right, next point. Right, obviously we're looking at what you call the sections and conic sections and things. Consider the surfaces. Now, there are these surfaces in R3 defined by the equations. F of x and y is 2 times the square root of x squared plus y squared. G of x and y equals 1 plus x squared plus y squared. And what shapes are described by F, G, and the intersection? What shapes are described by that? Okay, so we're looking at these two shapes here. This one here is a specific shape, and that itself, it becomes a specific shape. To see these shapes, it's something very, very easy. So let us analyze this. Right, so we analyze these as follows. And this one is our z, y, and x. Let us analyze f. Right, first things first, we can decide to annihilate and to totally remove y. Make y 0. In which case, therefore, you can look at these as x 0 to the square root of this. So you have x and 0. Okay, this becomes like the modulus. Okay, I want to mention these very clearly here as we move along. That you see, if we make y 0 and we have f of x and 0, and this is 2 times the square root of x squared plus 0. Take the square root, x squared. Square root of that is the modulus, which is f of x and 0. Okay, what happens here? If we want to sketch this one, so this one, because now you are looking at these in a plane where, for instance, y is 0, right? In a plane where y is 0, you can be talking about what plane, for example, because if you have this, you can view this as z, where z is the function of x and y. So if you view this as Z, for example, you're looking at things where what we have here, therefore, is the fact that the y is 0, so yeah, it is something in the zx plane. So we're dealing with the zx plane. Okay, so dealing with the zx plane, then what do we have? So you sketch this one. You sketch this one, the zx plane. So if you put this is like a modulus function, the absolute value function. So when x is 0, you have 0. When x is 1, you put here 2 times 1. Because x is 1, so the absolute value of 1 is 1 times 2. So it's 2. So when x is 1, z is 2. So yeah, you would have, let me use a different color, otherwise everything is just going to be red. So you're going to use green and graph like this. Okay, but the x-axis also proceeds the other way. Remember, this is like positive x and this is negative x. So you can also take -1, and then it's going to be, obviously, if you, put in the modulus, what I'm saying is, you can take x equal to -1 in this equation. So this is 2 minus 1, 2 times -1 like that. So at this point, what this produces is the fact that this is exactly 2. Okay, so -1 then produces a 2, and you also have this. Okay, so in other words now, and yes, please.
If x is 1, what is z?
Okay, if
Since y is 0.
yes, okay, yeah, because we are looking at it. It's to get the x-intercept, you make something 0. Okay, it's standard practice. So we just choose to make y 0. So we look at a plane where y is 0, and y is 0 in the 2-dimensional plane, which is the zx plane. Okay, but now, so if x is 1, put it here, because the formula we have created is f x is 0, and therefore it is 2 times the modulus, because the square root of x squared, is the absolute value of x. Okay, so you have 1 and 0, which is 2. So if x is 1, then you have 2, because the absolute value of 1 is 1 times 2, it's 2. And then now it's going to produce a v. This is called the absolute value graph. And then now, if simultaneously, if you decide to make x 0, such that y now is not 0 anymore, okay? So you decide to make x 0, y is not 0 anymore, then you're going to get other lines like that. And so what this thing is going to produce, it's going to produce a shape like this. Going to produce a shape like this. But this shape here is what we use to enjoy lots of ice cream. And this one here is called a cone. So in other words, this shape here is just nothing other than a cone. It is a cone. Because they said what shapes are described by f and g and their intersection. Okay, we're going to look at the intersection. But first and foremost, what then is very evident by just graphing is that this one here is a cone, and then we shall look at the other one. Let's look at part next. Okay, so we look at this one now. Okay, let's look at this one. What kind of a shape is this one? Okay, same thing. We go back to grade 10, high school. Right, so we're going to make one of them 0. So, okay, the way we do at university, we focus on planes, okay? And we're going to use that so that we can think like university people are not like school, although these things are just the same. Right, so we're going to say, okay, Mr. Examiner, this is Z. So the equation we're given, it's Z equals x squared plus y squared. Okay, that is what this thing is. You can write it like that. So at this point, If you then decide to say, okay, let us look at a plane where y is 0. So let's look at the zx plane. Zx plane, in other words, we remove y, which means that we have z equals 1 plus x squared. So when x is 0, z is 1. Okay. And then now you put, okay, we want to plot this graph, the graph of this. It's like in high school, if they say plot the graph of x squared plus 1. How do you sketch this one? Because it's the same thing. Okay. Obviously, in high school, we first, you can use many ways. The graph of y equals x squared is a parabola. Call it a parabola. But now if you add 1, it's going to go up 1 unit. So it's the same. But this one is going to be in the zx plane. There's nothing. So it's like you remove this one. And so you remove the y-axis, and which you can do in mathematics. And therefore, you have this here and that. So this is the sort of shape that you're going to have. Okay. And then now you do the same. So you remove x, and then you have 1 plus y squared. 1 plus y squared, you do the same. When y is 0, you're going to be z. It's x squared plus y squared. And we're saying now x is 0. So you have z equals 1 plus y squared. When y is 0, you have z equals 1. And then now y can be 1. So that in the end, then you have, if y is 1, then you have like 1 plus 1. Y is 1. 1 plus 1 is 2. So z is going to be 2 whenever y is 1. Okay, so you resuscitate. You bring this back. You bring this one back. So we're saying y is 1. And then you can also take y minus 1, because you're going in the opposite. Because this x is, right, we only show the positive, but the negative parts of this axis are on the other side. So now if x is 1 here, then z is 2. So yeah, we're going to have the graph like this. Okay, this is not tidy, but it is sort of giving us the idea that we need. So in the end, then the kind of graph we're going to have here is that one. So we therefore have this graph here. And then we have this here. Okay, so this is what we have. Okay, so in the end, we have this kind of a graph. What kind of a graph is this? So it is a parabola that is here like this, but there's another parabola that is on the other side like this. So there are many of them. So as a consequence, this one is called a paraboloid. It's called a paraboloid. So now it's called a parabola in high school, a paraboloid in 3 dimensions. Okay, so we continue. We continue. So that in the end, then we have the following. Okay, they said obviously, what shape are described by F and G? We've already seen that this one here is a cone, like an ice cream cone, and this one is a paraboloid. Paraboloid. Okay, right. So now, if this is the case, but now we need to describe we need to say what shapes are described by F, G, and their intersection. Their intersection. So the intersection will therefore be what? Okay, let us intersect them. So intersect them now. Let us see what happens. So you're gonna draw them on the same set of x's. Right? If you draw them on the same set of x's, you'd have the following. Right. So you'd have the four that here is this one here. The cone. Okay, just a different color for it. Remember the cone, we drew it before, but it is sitting at the origin. But this paraboloid starts at 1. Okay, but the cone sits at the origin. The cone sits at the origin. Okay, because the cone sits at the origin, we have the following. We have the following. Okay, so here's the cone, but yeah, it's gonna intersect. So we're at the point where they intersect. We have the following here as a matter of fact. We have the following here as a matter of fact. Right. So wherever they meet, you are able to see, therefore, that it is where f equals g, and we shall have a description of that. Right. To say wherever they meet, would have what? Right. Yeah, we'll discuss the point of intersection there wherever they meet. Because wherever they meet, you'd have what? Okay, so wherever this meets that, you have the shape of a curve. There's a curve that is sort of the boundary of these here. And that is where these two meet, and we shall obviously discuss that. But now this shape where that traces the point of intersection traces a circle, traces a circle, right? So wherever they meet, you therefore have a circle. The intersection is a circle. Right. This intersection itself is a circle. Right. So now we have described a cone, we have described a paraboloid, and we have described a circle as a point of intersection. Next point. The examiner goes on because the intersection itself is very detailed, and obviously we spare some time to discuss it now in the part B. And the examiner says, give a parametric equation describing the intersection. Give a parametric equation describing the intersection. So now, I mean, to describe the intersection here is as follows. To describe the intersection, we must say let. Okay, like in high school, wherever two functions meet, we like equate them to each other. And if we equate them to each other, we're gonna yar f equals g. So f it's 2 times, and this is x squared plus y squared, which is 1 plus x squared plus y squared. So this is what we do to find the point of intersection. And so simultaneously, we think like students doing this course, 2615 calculus in high dimensions. So we set R to be equal to the square root in line with Pythagoras theorem. Because when we're in high school, we're taught that R squared is x squared plus y squared, depending on how one remembers the Pythagoras theorem. So x squared plus y squared, you can make R the subject where R is positive. So we have only one square root. Right, so the above equation can also then be solved as follows. And because of these, then we have twice R equals 1 plus. So this here, x squared plus y squared from high school is the square of the radius. Okay, and this is the same as what? So it is R squared minus 2R plus 1 equals 0. So it is R minus 1 squared equals 0. So that then in the end, what do we have? So which means that we have R equals 1. So then we have the square root of x squared plus y squared equals 1. And in the end, we have x squared plus y squared equals 1. Right, so at there, what we then do, we proceed to then say, okay, this point of intersection itself becomes a circle. I mean, it is testimony and is testament to the fact that we spoke about the intersection as describing a circle, but we're looking at the geometrical presentation part of it than the actual algebraic presentation. Now we have an equation that describes the intersection of the two. So if you equate the two, then we have an equation that describes the intersection. Okay. All right. So then we have the following thing that we need to do here. Okay, but now, because the question now, we found the intersection is a circle because x squared plus y squared is equals to 1. And this is like x squared plus y squared equals r squared. And circles from high school centered at the origin. X squared plus y squared equals r squared is a circle centered at the origin. But we remember that we have x minus a squared plus y minus b squared equals the square of the radius. Okay, this also becomes a circle. Circle centered at A and B. So this one has the center. Center A and B, and this one has the center, the origin. So the examiner says give a parametric equation describing the intersection. So, okay, this is the equation, but we need to give a parametric. So we need to parameterize this. We need to parameterize this. We need to give the parametric equations. Right. So in other words, now to continue, to parameterize. So yeah, we got, okay, we just got x squared plus y squared is the square of the radius. Okay, we want to parameterize. We want to parameterize. So to parameterize, oh, okay, to parameterize. Okay. To parameterize circle, let's can write parameterize the British spelling with an S, but the Americans spell that with a Z. So obviously to parameterize, how do we parameterize this? Because that is the point of intersection, that is the intersection of the two curves here. And how do you then parameterize this? To parameterize a circle. So yeah, this one is a circle from school. To parameterize the circle of radius, or we use, okay, we use x equals r cosine t, and we use y equals r sine t. Okay. Okay. Because the circles are parameterized like this. Okay, you learned that. For t in the interval 0 to 2 pi, so you put square bracket here around there. And now we then say, and we know that this presentation, this equations here, this presentation does parameterize, right? So it does parameterize the circle. It does parameterize the circle because it does parameterize the circle. How do we know that this parameterization is correct? I mean, it does that because the x squared plus the square of y is equal to what? Okay, we square x. So yeah, it becomes cosine t plus r sine t, which is r squared cosine squared t, r squared sine squared t. R squared cosine squared t, sine squared t. And this is r squared. And the implication indeed is therefore that it is true that because we're getting that x squared plus y squared is therefore equal to r squared, and this describes a circle. So this implies that therefore what we then have is that x equals, so because this is equal to 1, it means therefore that the radius is 1. If the radius is 1, then you're going to put 1 here and 1 there in the place of the r. So that is 1 pi cos t, which is x equals cosine t, and y equals the trigonometric sine of t. Okay. And our t is between 0 and 2 pi, like this, round. Okay. So this is, because we're supposed to give a parametric equation describing the intersection. But finally, let us say more about this. Finally, note that z is z written as x squared plus y squared equals 1 using the equation. The equation of the paraboloid. Okay, the equation of the paraboloid. So the complete. So the complete parametrization of the circle where the two graphs intersect is cosine t, sine t, 1. T lies between 0 and 2 pi. Let's look at what this means. So we're saying finally note that z equals x squared plus y squared plus 1 here, plus 1 here. So we are noting therefore that finally note that z equals x squared plus y squared plus 1. Okay, this one, as we said, we can use z to label these things. To label these things. So we continue. So in the end, then right now we have f equals this. Okay, I was saying that. So z is 2 times the square root of x squared plus y squared. And here, z is 1 plus x squared plus y squared. Okay, yeah. So, I mean, we finally note that z equals yeah, we can write it as 1 plus x squared plus y squared, but you can also write it as x squared plus y squared plus 1 using the equation of the paraboloid. So the complete parametrization of the circle where the two graphs intersect is this. So obviously, because we can see the paraboloid contains a couple of things, right? So, right, okay. So yeah, and then if we put these ones, this one here is going to be exactly the x and the y, and you can square. I mean, what we're saying here is there's going to be an x and a y, so you put them here, And you can square cosine squared plus sine squared, which gives us a 1. And then obviously, if these two gives us a 1, this would mean it agrees with the intersection where it says that x squared plus y squared equals 1, which is the point of intersection, right? So indeed, the x and the y themselves remain correct. Remain very, very correct. Right, so that then in the answer, yeah, I want to remove this one, please. Okay, because in this discussion, we need to note a couple of things, but yeah, we need to know that t, yeah, but I want to use the other notation, the interval notation. We can use this inequality, but we can use t as an element. T is an element of the interval. So we can then say t is an element of the interval. We include 0 and 2 pi, because see, the thing is that 0 and 2 pi, both of them are here, 0. Pi over 2 radians, also called 90 degrees, 108 degrees. Yes, please. Also called pi. Yes, please, ask your question.
Oh, you mentioned that the intersection was x squared plus y squared equals to 1, and through the calculation we calculated the radius, which was 1.
Yes, yes.
My question would be, because it's a circle,
Yes.
there's sometimes like you could get like a circle being 2x squared plus 2x squared equals to 1,
Okay, okay. Yes, yes.
Yeah.
Like, did you say
So
like 2x squared? Yeah.
plus yx squared. So
Yes. So you can
those
put the
two.
same numbers here. Yeah. Mm-hmm.
Oh, it doesn't matter.
Yes, I mean, you can put the same numbers. Well, I mean, it depends on but the second is going to be a different one to this one. I mean, if you put 3, like, suppose you put, there's a 3. This one is also a circle,
Yeah.
this, you know?
Yeah.
But
Yeah.
this second is different from that. How?
Yeah.
How is it different? Well, it is different in terms of a circle means that, okay, a circle means that you have the same coefficient of x squared and y squared. Because now, if you proceed to divide by the 3, then you can have like x squared plus y squared equals 1 over 3. You get the point? So in the end, then this is what we have. Okay, so this becomes a circle of this radius and is centered at the origin. So, yeah, but yeah, I mean, there are many circles there, but we got a radius 1 here. We could, because it was the intersection was this, was x squared plus y squared equals 1. And it was because the radius, we got radius equal to 1. Okay, and therefore we know that radius itself, we know that if we have radius is 1, because we use the transformation r equals the square root of x squared plus y squared. So we got r equals 1, I mean, we got x squared plus y squared equals 1. Okay, so that's what we got. And therefore, we are able to get, to parameterize the circle of radius r, we use x equals these. For t element of 0 to 2 pi, these does parameterize the circle because of these, and we're able to get that is the answer. Okay.
Okay.
Yeah. Any idea? Any question? Because we can say more about these things, but I was trying also to say that I mean, there are many equations you can have. Like, let us look at this one: 2x squared plus 3y squared equals 1 or 5 or anything. I mean, these numbers can change depending on the question, obviously. But this one, for example, this is a circle because the x squared and the y squared have the coefficient 3. But this one is not a circle because the x squared and the y squared have coefficient. This one 2 coefficient and this one is coefficient 3. So this here would not be a circle. What shape will this be called? Okay, this one is called an ellipse. Okay, this one is called an ellipse when so it's like oval. It's oval, you know. So this one is called an ellipse, or in ellipses either this way or the other way. It's like, it's in the shape of an egg. But after the circle, if these two numbers are the same, so it becomes a perfect circle like this with a radius from the center to the circumference. Okay, so but okay, what were we doing in all these things here? All these things we've written. What is the purpose of this? Remember that the question said give a parametric equation describing the intersection. So we've seen therefore that we've given a parametric equation that describes the intersection. And this is the parametric equation that describes the intersection. Right, and it is exactly this. So we're done with it. We're done with it. And this is the answer. Think about this and make sure you obviously understand these here. Make sure that you understand these. Right, make sure that you most certainly understand this presentation because it is very, very significant. It is very, very significant. But yeah, we're gonna say a little bit more. Okay, let me just say something on something. I'm just looking and just thinking. Also, look at the fact that this parameterization is correct. And it is a parameterization of the point of intersection of it is describing the intersection. What does it mean then? Because you need to test. You can test this here. You must substitute. You need to substitute into the equations. If you substitute into the equations, then you'll be able to see if this is satisfies the equations and makes them true. Okay, let us test that because we're just looking at these there. So if you test by substitution, therefore, you must be able to get the result. For example, if you then realize that whatever you have at this point is the fact that we have x and y and you plug them in here. Right, so if you have x and y and you plug them in there in this, so you'd have that this 1 plus, and therefore you have your x is cosine squared t, and then you have your y here, sine squared t, which is 1 plus. What is cosine squared t plus sine squared t? Is 1, which is equals to 2. So you get a 2. But also, when you put the x and the y, you'd have 2 times the square root of cosine squared t plus sine squared t, which is cosine squared plus sine squared t, which is a 1. And this equals 2. So this equals 2 and this equals 2. Okay, you're able to see therefore, yes, please.
So what is the one in the parameterization equation? Like that one after sin t?
Yeah. Now I want to obviously make mention of that fact and the fact that this one here. Okay, I want to mention the fact that this one should instead be 2, strictly speaking. It should be 2 because if you put in everything here, you're able to see that we're getting a 2. Because this is the z component. Okay, this is z equals. Okay, it's wonderful that you noted that. So that you have 1, 1 for the r, and this is the z. But if you see that if you substitute here, you get a 2 and you get a 2. So yeah, it makes sense to, it is in particular correct to put the 2 there. Why? Because if you put in the x and the y, you must get z. And if you put in, like in any of these, because it has to do with the intersection. So you put in the x and the y, you must get z. Okay. If you put the cosine and the sine and you square them, you get you get 2 in each of the equations. So yeah, we need to safely make z equals 2 because of that. So we have obviously noted that as much as the radius is 1, and you can leave that out, but the z must be 2 exactly. Any question? I'm sure that we pretty much have spent some time on this question. And right, because we've given parametric equations, so the correct parametric equation must be cosine t plus, or sine t together with 2. Right, together with 2. Please note that. But the radius indeed is 1 by calculation. Right, so any idea, any suggestion, any input, any comment, any remark, anything? Then we move to the next question. Okay, we started here and we're cruising. Any input? Maybe you think, okay, yes, please.
So at the beginning, just after getting the radius, we
Yes, at the beginning.
noted that the parameterization of a circle is xy. I mean, x equals to r cos t, y equals to
Yes.
r sin t. So
Yes.
therefore, z equals to z. I could note that in my
yes,
notes.
yeah. Okay,
So
yes, so well, I mean, to parameterize any circle, if we use x equals r cosine t plus together with y equals r sine t. Why is the circle having cosine t plus sine t? Because these cosine t and sine t, they satisfy the equation of a circle. What is the equation of a circle? Okay, we wrote it here. We said the equation of a circle is x squared plus y squared, which must be equals to the radius squared. Okay, so if you put in the x, which is r cosine t, and you put in the r sine t, that is what? It is the sine, the inclusion of the cosine and sine that is going to produce r squared here, because the cosine squared plus sine squared equals 1. You get the point. Think about it. Yeah, your suggestion, your thought. Okay, because I'm looking at the figure. So yeah, to parameterize a circle, we use this. Why? Because this is the explanation for that. Because the equation of a circle, once again, is x squared plus y squared is what? Is r squared. And it is only that if we choose x to be r cosine t and y to be r sine t that we're able to get r squared here. Because you substitute x equals r cosine t, y equals r sine t, and then we have r squared cosine squared plus r squared sine squared. Then we pull out the r squared here. We have cosine squared t plus sine squared, which is r squared. You get the point?
yes, that part I understand.
Okay. And therefore, the substitution we're suggesting, because you see, the question, I mean, in the true sense of things, the parameterizations can be many, but this is the easiest one. Okay, there are many parameterizations somebody can choose, but for circles, we use cosine t and sine t because we know that cosine squared plus sine squared is 1, but somebody can choose other parameterizations that make this equation true. In particular, you can guess others as well, but I wouldn't want to go to more general, other specific cases of reasoning that are not popular, because any expression of x and y can be chosen such that the answer is 1. You can choose anything so that the answer is 1. What else can you choose? Okay, but yeah, see, this is the most popular. These are continuous, and these are the best ones. But somebody can choose others. As long as when you square the x, you square the y, you get to 1. But you see, I would not want to motivate that because it can be potentially controversial. Somebody might think, hey, you're thinking differently from everybody. Why? But a parameterization means that make a choice of the x and y so that the result is 1. Okay, the easiest we can choose ourselves is cosine squared plus sine squared is 1, and this is standard reasoning. But you can make other choices. What other choices can you make? I would want to, yeah, because for instance, somebody can come and say, you choose, yeah, in terms of parameterizations, you can choose this one to be, for instance, the square root of t and y to be, so this is going to be restricted. Okay. You can choose this. Okay, yeah, but this is not popular because if you put them here, they give 1. So I'm just trying to make sure that the mind is open in terms of that it's not everybody can think it the same way, because these parameterizations are suggested expressions of x and y. So that I'm saying you choose, somebody can come and say, okay, I can choose this ones because they make the equation true. Okay, and therefore, if you choose these ones here, but yeah, we choose the x squared and y squared because they are popular and they are circle, and the circles themselves contain the things. The circles themselves have radii, and the radii are very visible from that. But if another student chooses x, y plus that, okay, with enough restrictions, you can have that. But I wouldn't want to go to it because we need a restriction for these, that t must be, this square root will have to be defined always, because otherwise then you'd have negatives under square root. But okay, if you square these things we're giving now, we're getting what? T plus 1 minus t equals 1. Okay, so this becomes the answer. Okay, then getting 1 still. So in the true sense of the world, somebody can come and say, okay, I suggest this parameterization, but now let's put a restriction on t. That t can potentially be 1, yes, but it has to be less than 1 as well. Less or equal to 1, because yeah, if it's less than 1, like t equals half, 1 minus half is 1/2, and you have the square root of 1/2. So you have this here. This can potentially be suggested one, but yeah, I'm just trying to say we can't think in the same direction, but I'm trying to make sure that understand that in particular, these become the best standard trigonometric functions for circles. Please, yeah, we use these to parameterize circles, but always because the mathematicians found them to work. And they found them to work because the circles themselves, this sine and cosine that derived from a circle, because they're derived, instead of them calling, instead of the mathematicians calling them like trigonometric functions, you see, instead of calling them trigonometric functions, you can call them secular functions. Why? Because these trigonometric functions are also called secular functions because they are derived from a circle like this. From school, whenever these things are done, I remember my teacher drawing something like this when I was still in grade 10 myself. And now coming to the point of saying, okay, there is a point, this x and y point on the circle, and you can be able to do that. Okay, I want to do something. Okay, these functions are drawing a bigger circle like this, and you can be able to draw a point on the circumference of a circle and then you have these, and then we have x and y, and then you have r like these, so that in the end, then you have exactly that. So right. So in the end, then, I mean, my teacher drew these, and now, okay, I want us to just recap on these. And then now, obviously, this becomes a triangle there. And then now, from this triangle, we use Pythagoras. And Pythagoras will tell us that x squared plus y squared is r squared, because it's a right angle triangle. So the square on the hypotenuse is sum of the squares on the other two sides. I mean, we are able to draw this kind of a thing and make sense of this in the most wonderful of ways. But obviously, yeah, what are we trying to say with this? We are trying to justify the use of sine and cosine in the parameterization. To parameterize any circle, we just simply use cosine t. We use t most of the time. And we also use y equals r sine t. So we have the following. We have the following. So that then in the end, what do we then have here? But now the t is, we include 0 and 2 pi. I will try to explain why the brackets, one is square like this and the other one is round. And this is because you have 0 degrees, yeah, but we use radians here. So yeah, the degrees, we leave them for school. And then we use here in this course radians, no degrees in 2615. So we use 0 radians. And then we have pi over 2. You have pi. We have 3 pi over 2. And then we have 2 pi. Okay, so that in the end, then what we're then getting is the following. So we're able to see therefore that this is 0 pi over 2 pi this. Okay. Okay. I wanted to bring to light the fact that at this point on this positive x-axis, these two 0 degrees and 2 pi or 0 radians and like 2 pi radians obviously intersect. I mean, they occur on the same ray. And because of that, then we must, we have our principal argument. So the principal argument would be something called the principal argument. So the principal argument here is going to be what? Well, the principal argument is going to be, it's going to be exactly 0. So in a situation where we have a dilemma, we need to make a choice because either the angle is producing, we're getting 0 degrees, we're getting like 0 radians, we're getting 2 pi radians. What is the correct answer? Okay, our principal argument is 0, which is the least one we can choose. Which is the least one we can choose. And obviously this becomes sort of our reference angle. It becomes our reference angle. Okay, I'm just mentioning this because, yeah, so we say between 0 and 2 pi, when we start measuring here in a counterclockwise direction, 0 is our least angle of measurement and it is our reference angle. And relative to these two, 0 and 2 pi, but obviously a full revolution would be 2 pi radians, and 2 pi radians, I mean, we know it is 360 degrees in terms of degrees. But now I'm trying to say, and I'm trying to bring to light that we would choose 2 pi, would choose 0 over 2 pi there. So, okay, and I'll mention this, okay, in passing, in summary, before we look at the next question. The principal argument story in mathematics is very important. Although in this course, it's not very, very poignant. Okay, now you can have, okay, so there are 2 ways to measure angles in mathematics, at least, either clockwise or counterclockwise, okay? Either clockwise or counterclockwise. We know that bearings are measured in a clockwise direction. Okay, now this is your radians, and then this is pi over 2, and this one is pi, and this one is 3 pi over 2. And this one is 2 pi. This is when we are going like this. And we're going against the clock. And this kind of motion is counterclockwise. It's against the clock. Or anti-clockwise. Counterclockwise. Also called anti-clockwise. Okay, but it's not the only way to measure angles, because we can start from 0 and go clockwise, like a clock. Okay, every time we start here from 0, we go here, and this is minus pi over 2. We go here, and then we have minus pi. We go here, and this one is minus 3 pi over 2. You come here, and this is going to be like minus 2 pi. So either 0, 2 pi, or minus 2 pi, depending on the direction of measurement. So clockwise becomes negative, okay? Now, because of this story, we can define our principal argument, which is going to make a lot of sense when you do mathematical analysis. Okay, we can say if you have two angles, okay, because here there are 2. Like here, this one is either pi or minus pi, you know? So because of that, then we say the following. Okay, I'm going to say that here. Okay, I want to mention the principal argument, sorry, a little bit, because we just have this parameterization and it's making us to mention too many things, but yeah, we shall conclude that. But these questions are not going to change substantially, please. When you do integration, the section called integration, they're going to come in when you do like our Stokes integration, okay. Right, using the Stokes formula, etc., etc. But I want to say about the fact that, okay, theta There's a case where the principal argument story comes in. Now, when we have these angles here, because either to get to pi, to measure like 180 degrees when pi is like 180 degrees. So we can either go counterclockwise like this, getting a positive pi, or we can go like a clock, like clockwise like this, and you get minus pi. But obviously we say we would choose the positive sense in mathematics over the negative sense. We would choose because if somebody says, okay, there are two angles here, pi and minus pi, so which one should I choose if I have that dilemma? Okay, so we choose the positive sense over the negative sense, and this becomes the principal argument. Okay, it is called the principal argument interval. So it is in this interval. So the angles in the principal argument must satisfy this guy. So we choose positives over negatives if the angles are between minus pi and pi. Simultaneously, we choose, okay, if this makes sense. This is a very secular kind of discussion we have. So simultaneously here, we are saying that if we are to see that 0 and 2 pi are on the same ray, we would prioritize 0 over 2 pi for least angles, because somebody could say, okay, but 0 and 2 pi are on the same ray, and therefore I can say the angle is 2 pi, even if I've not traveled across. Well, because they're on the same ray, are they not equal to each other? Well, the truth is, obviously, in terms of the positions, they are on the same ray, but you prioritize 0 over 2 pi. That's the story we're putting across. I'm sure that we can have the debate on this one. We can have a huge debate. We can have a huge debate. So we continue. We continue. We continue. Okay, yeah, I'm just, let's look at the next question. Let's look at the next question. Right now, look at the next question. We have the following story. We have the following story. I would like us to look at this question about first principles. Now consider the R2 to R function f defined by this. Okay, here is a multivariable function, a function of two variables. Bivariate function. Bivariate function. Two variables. Bi for two. Okay, now from first principles, okay, we need to prove from first principle that this limit of f of x and y, as x and y tends to 0 and 0, this limit equals 0. Hint, note that x squared is less than or equal to x squared plus y squared. So we have the following. We have the following. Okay, let us do this one. Let us do this one. So then we have this here, which is okay, I want to start like that, but let's start as follows. Let's just describe these first. Let's describe these. So, I mean, to sort of describe these, we proceed as follows. Okay, we start by saying given. Can write here. Given epsilon positive. Given epsilon positive. We must find delta positive such that if 0 So that if 0 is less than, so come here. So if 0 is less than the modulus of x and y, less than delta, then, okay, yeah, let me write a bit clearly here. Then, okay, such that if 0 is less than that, then the modulus of f, x, and y minus, so yeah, you take the f of x and y minus 0 is less than epsilon. So yeah, this is how we start the first principles proofs, because we must prove from first principles that this limit is 0. Okay, so to prove that, I mean, we, yeah, we start like this. Given epsilon positive, so we start with epsilon. Epsilon positive, we must find delta positive such that if 0 is less than delta, then this is less than epsilon. Okay. Okay, so what is f of x? Okay, we substitute. Okay, you can use, yeah, I want to make sure that we put some wording here. So thus, or now, you can use now. In mathematics, to bring a very important argument, you use now. We use now. Okay, just allow me please to say that. So now we're bringing a very important step. All right, now you start. We always start from this part. So we start with the modulus of the function minus the limit. And then we substitute the function, which is this one. Minus 0. Okay. This is what we get. But we know, remember the hint. The hint. What is the hint? The hint is saying, so you're, okay, yeah, if we're subtracting 0 here is the same as subtracting nothing, so we can just write like this. This is less or equal to x squared and y squared. Yeah, x squared is less or equal to x squared plus y squared. So we perform a substitution here, and we have that. We have this. So x squared itself is less or equal to x squared plus y squared. And therefore, this is what we have here. But now in mathematics, if you have x over the square root of x, power 1 there is the same as x to the power 1 minus 1/2, because the square root is 1/2, meaning it's x to 1/2. So we can use that and say, this is like, so dividing x by its square root, dividing x by its square root, is the answer is the same as the square root of x. So this is going to be the same as the square root of x squared plus y squared. We agree that the absolute value is still there, the modulus is still there. Okay? Like so. Now, what is this? What is this? This is nothing other than, so it's in green color. Thus, we have that the f, x and y minus 0 okay, is the modulus like this, but you can even remove the modulus because the square root is positive by definition. It's unique. So, sorry, it is positive. Okay, this is Pythagoras theorem again, coming in another form. So the length of a vector is the square root of x squared plus y squared. It's a definition. But this thing here, the modulus of the f of x and y minus 0 is less than epsilon, but also you have that this modulus is less than delta. We are in business and we're done, because we can then say hence. We're looking for delta that depends on epsilon, so delta equals epsilon. Okay, by comparison, because this thing here, the modulus or the length, okay, call this the length of the vector x and y is less than delta, but this one is less than epsilon, so we are able to see therefore that, okay, comparison. This in the statement is less than delta, but the same thing, the length of the vector is less than epsilon. So it means that this delta is equal to this epsilon, because in mathematics, we reduce this one to the same thing as this, and we managed to do that. And so that at this point, it means, therefore, that our delta equals epsilon. Delta equals epsilon. Our delta equals epsilon. Our delta equals epsilon. Okay. Because we given epsilon positive, we must find delta, and we found delta, and delta equals epsilon. Now, and we found delta equals epsilon, and therefore we write the following conclusion. I'm gonna write it here. And this is the conclusion. Therefore, the limit of the multivariable function as x and y approach 0, 0, this limit is 0. Okay, we have solved this problem and we have answered this question in detail, and we are through. We are done. Let's look at the next question. Okay, in this question, because the previous one was question 4, and we've already proven that in terms of the epsilon delta notation, we use the epsilon delta notation to prove, and we have proven that this limit is 0. Now let's look at the next. Okay, in question 5, you consider the R2 to R2 function. Okay, R2 to R2 function, and this is very interesting. This one was an R2 to R because it takes a pair to a number. Now here, this one here is R2 to R2, so it takes ordered pairs to ordered pairs. You see, the output is an ordered pair, but also the argument is an ordered pair x and y. So yeah, R2 to R2. So use limit rules to determine the limit of this guy. Use limit rules to determine the limit of the function. So we want to find the limit as x and y tends to pi over 2 of the function. Okay. So we have exactly that part. We have exactly that part, and then we say it is exactly the limit of the other guy. It's exactly the limit of the other guy. Okay, limit as x and y tends to 0, or tends to this one, by pi over 2. We recall something, that this f of x and y is this. So the first argument is y, trigonometric sine of x divided by x minus pi. The other one is xy over this. Okay, we're going to have to do something here. Okay, just write clearly like this. Okay, so yeah, something like that. So, okay, now let's look at this here. Okay, yeah, we have this. We just want to find the limit of this function. As x and y tend to pi and pi over 2 respectively. Okay, so yeah, it's a multivariable function we have here. Okay, now in mathematics, we're allowed to take this limit and put it inside this function. So that is what we can do. So when I have the limit as x and y, okay, we can put the round things here, round brackets, round parentheses, or these equals. This is y the sine of x divided by x minus pi. And then now pi over 2 here. Okay, this one tends to pi over 2, and then we have xy sine y. Okay, yeah, I mean, take note of this. What have we done? We've just taken this limit and we put it inside the arguments. Okay, these are the limit rules, because we need to use limit rules to determine this, and it is a limit rule to allow these limits. So you can put the limit inside the function. You can do this. You can put it under the square roots, within the parentheses, and so on and so forth. Now we think, when we get to this point, to say, how? What do we do now? Because you must get the answer to this. Okay, in limits, what we do, we always substitute straight away and see if there's a problem with that. Okay, if you put x here, this is like x goes to pi. So you put x here, it's going to be pi or minus pi, which is 0. And this is immediately a problem. It's division by 0 pi. Just check the numerator. Okay, if you put x equals pi sine pi, which is like sine 180 degrees, and the sine 180 degrees is 0. Who is 0 over 0? And this requires something we call L'Hopital rule. But hang on. L'Hopital rule, this is a multivariable function. L'Hopital rule applies in first year when we are doing functions of single variables. Okay, we can differentiate with respect to x, but what about x and y? How would you differentiate with respect to two variables? Okay, we reason this. Here, let's come to this side, because we check this side, this part. X and y, so y is pi over 2, so you have the sine of pi over 2 here. What is the sine of pi over 2? The sine of pi over 2 is what? It's exactly 1. And this is good, because the sine is defined. The top is pi over 2. So you have pi over 2 over 1. And this one is okay. This one is all right. All right. Okay, y'all just take note of these here and we're good. So the only problem is this side here. So let's face the problem. Let's face our fears now and tackle these. So this is then the limits, okay, within the parentheses. And obviously the thing we need to brainstorm our way out of is, what do we do with this part? Because here we substitute, everything is defined here. So we can just put in the x and the y, and we're going to do that. So yeah, we're going to deal with this other one. So let's deal with this. So we have the limit. So we have the limit as x and y tends to pi over 2 y sine x divided by x minus pi, and then we have the limit x and y simultaneously tend to pi over 2 xy divided by sine y. So we have the following. Now, at this point, okay, let's look at this one. So The problem is this one here. So is the sine x over x. So we're gonna perform a split. Okay, it's gonna be a long chain. So it is right at the bottom here because it's gonna be a long chain, and it's gonna be as follows. So this is gonna be the limit. Xy tends to pi over 2. And then we have y. And then we split it up. X and y tends to pi over 2 sine x over x minus pi. Okay, so we have split this one. The y is on one side, and the x is sine x, and the x minus pi are actually on one side. So we're good. Now this part here is everything is okay because yeah, x and y. So x we put pi. The y we substitute does not yield to it does not yield undefined things. So we can just evaluate this limit straight away like this. Now let's come to this part. Okay, now when you come to this part, yeah, this part is easy. Yeah, because you take the limit of y alone when x and y tend to pi and pi over 2. So at this point, y is pi over 2. Y is pi over 2. So yeah, y is pi over 2 here. So it's going to be pi over 2. So the limit is just going to be pi over 2 because there's no x here. Now we come to this one. This one here now would be, if you substitute straight away, x, it's sine pi, sine 180, it's 0. If x is pi, then you have pi minus pi, which is 0. Woo, it's 0 over 0. And 0 over 0 is undefined. So we need to think afresh. What do we do now? Because it's 0 over 0, and 0 over 0 is indeterminate. It's what you call, it is undefined. It is what you call the indeterminate form. What are the indeterminate forms? We'll remember from calculus 1. 0 over 0, infinity over infinity, 0 times infinity, and so on and so forth, amongst others. It's also infinity minus infinity, because infinity minus infinity is undefined, but it is not 0. It is not 0. So at this point now, we have 0 for 0. So we differentiate the top, which is the limit, is x, y approaches pi over 2. What is the derivative of sine x? Which is cosine x. Okay, the derivative of sine x is cosine x. And then we okay, the rule we're going to use is something we call L'Hopital rule. It's called L'Hopital rule. So we're going to use L'Hopital rule. So differentiate the sine, getting a cosine, and then differentiating the bottom, all of it. So we do dx of the top, sine x, we divide by dx of x minus pi. Okay, the derivative of the top is cosine x, the derivative of the bottom is a 1. And this one now becomes the pi times pi, which is exactly pi squared over 2. The sine of pi becomes a 1. And then in the end, then, okay, this one is a times, please. It is a times. Note that one. It is a times. So we have a times here, and this is cosine of the x. Put the x here. It's pi. It's pi, and this one here is pi squared over 2. Hello, my dear. Okay, we're finishing this one just now. Just a second. Okay. Hello, my dear. Yes. Okay, thank you, my dear. Oh, all right. Okay, that's fine. Okay, Klaufer, my dear. Thank you, my dear. Okay, we're ongoing. We're just speaking to someone. Okay, I'm finishing. We're finishing this one. The next minute is done already. Let me just see if I can help this person out with just knocking here. See what we can do. Just 1 second. Hello, my dear. Yeah, maybe obviously I can't say it. Look.
Okay, yeah.
All right, thanks, my dear. Okay, all right, we're right back. We're right back. Sorry, I was just speaking to somebody who was just knocking on my door here. Okay, now this cosine pi, what is cosine pi? Cosine pi is like cosine 180 degrees. Okay. So cosine 180 degrees is the following. Right, so cosine 180 degrees is a -1, and this one is pi squared out of 2. So minus pi over 2, pi squared over 2. Okay, and this is the answer. So in a nutshell, we've been able to therefore, and we can therefore be able to make the following conclusion. We can be able to make the following conclusion and then say hence. Hence, x and y, which is pi over 2 fxy, this here is minus pi over 2 pi squared over 2, and this here is the limit that they wanted. It is the limit that they wanted. The limit they wanted. So y'all look at this and sort of reason these out. Reason these out. Reason these out. And we're done with this question because we use limit rules, like the L'Hopital rule. We use that one. And we also allowed this limit to, we also allowed the limit to get into the actual arguments of the ordered pair. Okay, good. Good. Okay. So we're done with this one. The next question is question 6. The next question is question 6. So in question 6, we're saying consider the R2 to R function f defined by f of x and y equals that part. And we're asking the question, and we are saying, write down the largest possible domain d subscript f of f. What is the largest possible domain of this function here? Okay, it's very easy to see the largest possible domain of this function. So we're going to note that the largest possible domain is the domain of f, which is in multivariable calculus is the function is a function of 2 variables x and y. So this is going to have the ordered pair x and y, such that this is an element of R2, such that x is not 0, y is not 0. X is not 0, y is not 0. Okay, so this is what we have. Okay, now look at this, and this is the largest possible domain. And this domain can be written in many ways. Another student can comment, okay, why? Because we are dealing with a rational function, and the only problem would be when the denominator is 0. For the domain, we need to perform restrictions such that the domain, rather the denominator, is non-zero. So at this point, which means that you have x, y, elements which are this x and y is an element of R2, such that x and y, this here is not 0 and 0. So the x and y cannot be simultaneously 0. So and that would be the largest possible domain of the function f. Okay, next point. In the next question, we need to show that the limit of f of x and y as x and y approach 0 and 0 does not exist by considering limits along relevant curves for 5 marks. So we need to show that this limit here does not exist. Let's show that the limit does not exist. And that is our next journey. We investigate that part. We investigate that part. And we say, this limit does not exist. How? We need to show that this limit of this function does not exist. We have with us the limit of x and y, which approaches 0 and 0. Okay, this is the limit of f at x and y. And this here, and this is 2xy squared divided by x squared plus y squared. Okay. We need to show that this limit does not exist. So, okay, by considering limits along relevant curves, so we're going to choose a curve and say along. Along, for instance, along curve C. Yes, please.
What makes a curve relevant?
Okay, that's a good question. What makes a curve relevant? A curve is relevant if it passes through these points that x and y approach. So x and y actually both approach 0 and 0. And so a curve is relevant if it is satisfied by this point, or this point satisfies the curve. Okay, so we're going to just investigate that one. So for instance, we're going to choose the curve y equals x. We're going to choose the curve y equals x. So along curve C, which is y equals x. Along curve C, which is y equals x. Okay, we're choosing the curve y. Because even if you draw these, the line y equals x passes through the origin, passes through the point 0 and 0. So this one indeed qualifies to be a relevant curve. But you see, somebody cannot come and say, you can choose the curve x plus 3, because it does not pass through the origin. So you need anything that passes through the origin. Like you can choose y equals x squared. Okay, that one is going to work. So here you are at liberty to choose anything. But yeah, this one cannot work, but y equals x can work. Y equals x squared can work. You can choose the parabola because the parabola sits on the origin. So yeah, you can choose that one. Okay, we're good. So we're in business now, and let's continue to perform our substitution. And this is most certainly what we do. And what do we then do? So we take the limit. Is the ordered pair of x and y, and these approach 0 and 0. Okay. All right. So, okay, now this is going to be the limit as this approaches 0 along the curve C as follows. So, which is 2x y squared divided by, okay, that is f, which is 2x y squared divided by x squared plus y to the 4th power. so that you have y equals x. Okay, now, okay, yeah, we good. So let's just remove something here. Let us remove, and I want to write a trivial step here, but very significant. So because we know that y equals x, so wherever there is y, you can put x. And this approaches 0 and 0 to x. And wherever there is y, you put, yeah, we substitute. Wherever there is y, you put x. Just chose this one. This curve, y equals x, because it's a relevant curve. So yeah, wherever there is y, then y, here there's y, so you put x, so it's going to be x squared. And here also, there's going to be x to the 4th power. So now this is x, and x approaches 0 and 0, which means x approaches 0. Which means you have this then, which means that you have x squared plus x to the 4th power. Okay, we have this limit now, we just need to simplify it. Okay, we need to just simplify this limit. Let's just proceed to simplify this one, multivariable function. So with the limit, x approaches 0. Getting x squared out of this, of the top. Okay, we can get x squared out of the top. Doesn't matter. We get x squared out of the bottom. 1 plus x squared. Okay, don't care what you do with the top. I mean, you can leave the top like that. Because, yeah, it's easier still, and it's very clear. So it might not really factorize the numerator, so you can be able to simplify these. But upon careful examination, we're able to see. Yes, please.
Sir made a mistake.
Where?
At your first line of equation, you said x squared plus y squared.
Let me see. Oh, because it must be y to the 4th power. Thank you so much. I can see your eyes are open, which is wonderful, right? So it must be 4, right? Thank you so much. It must be a 4 here. Because, yeah, I agree. It's x squared plus y to the 4th power. So, yeah, but I'm glad that was rectified here. Maybe because I looked at it from the question. Right, so obviously it is x squared plus y to the 4th power. But obviously at this point, we replace every y by x so that, yeah, wherever there's y, then you have x squared here. And then here you have x to the 4th power, okay? Right, so 2x by x squared it is indeed 2x cubed. And here we factor out x squared from the denominator. So, okay, we're good. Now let us simplify. Once you do it in green color, x squared is going to cancel in x squared, giving us a 1. Giving us a 1. And now we can be able to finish this off at the top here. You can be able to finish this at the top over here, and we're able to see, therefore, that this is the following. Right, so we have the limit as x tends to 0 of 2x divided by 1 plus x squared. Okay, because this x squared has removed one factor of x squared from the x cubed. So, yeah. Okay, so this would therefore be equal to this. Okay, let's now we check. Is there any problem if we substitute? We take the limit straight away. Okay, we use the language taking the limit. So if we take the limit here, we'd have 2 by 0 divided by 1 plus 0 squared. What is the answer? Okay, 2 by 0. 2 by 0 at the top is going to be 0 divided by 1, and it's a big 0. Okay, and therefore the implication is that we have the following. We're going to come and then say, hence the limit. Xy approaches 0 and 0 of the curve C. Can even put C here. Along C of f, x, and y, we've seen that this limit is equal to what? This limit is equal to 0. So we're going to do another one along curve D. We normally use C and D, okay? Just two curves that are gonna prove these become very enough. The next one you're gonna guess is another relevant curve. So along another curve, let's use along curve D, which is y equals x to 1/2. X to 1/2. Okay, now if you use x to the power 1/2, then let us do that. So you have these. So now then we have the limit. Okay. Along C, along D. Yeah, is that the D? Is it the D you're noting? I'll allow you to comment there because you're using curve D now. Yeah, that was your point, right?
No, I wanted to ask a
Yes.
question.
Yes, please.
I remember you saying that once they ask us about relevant curves, ne, we
Yeah.
can choose any curve, ne?
Yes. Any
I
curve.
mean any curve that satisfies the limit, ne?
Yes. Yes. Yeah.
What if I have more than two? Should I include it in my answer?
Yes. But now we just need
Like
yeah.
maybe I have more than
More than two curves. You mean more than two
yeah.
curves?
Maybe I
Yes.
have like three curves.
Yes. You can
Should I
include
include
three.
them in my
Yeah. You can
answer?
include three. Yeah. But it's just that
Okay.
two become like very enough. Like let's yeah. But you can use any number. You can use yeah. I mean, the more you use, the better. But doesn't mean you need to fill because it's just 5 marks. You see, in the exam, so you can't fill your exam book with one question doing too many curves there. But I mean that will be correct. That'll be correct. Okay, right. So now let's write this one. So the f function is this one, f of x and y. So this is 2xy squared, and this divided by x squared plus y to the 4th power. Yes, please.
Is there a curve like where it's like x is the subject of the formula?
Yes. But it's just that it's easier to, okay, yeah, I get your point. Yes, you can have a curve because here, like, x is the subject of the formula, the one I chose, because it's y equals x to the 1/2. So it is actually the same as the curve where, okay, because it is the square root. It is the what? It is the square root. So it is square root of x like this. So if you have y equals square root of x, what do we do with these? So in mathematics, if we have the square root, we can square both sides of the equation, getting y squared equals x. Y squared equals what? X. So yeah, this would be a curve like that. But it is common for us to choose the y equals. But obviously, you see, if you choose this one, if you write it like this, that would mean that wherever there is x, you must put y squared, which is possible. You can do it like that, you know? And therefore, the answer is going to be correct. So, yeah, okay, so you're going to use y equals the square root of x, because the square root function is what? Okay, it's yeah, so this one can be y equals the square root of x. You can square both sides and write it as y squared equals x. What kind of a graph is y squared equals x? This is a graph where now x is y squared, but if you square any real number, you get something non-negative. So it's going to be on 0, but also it's going to take the x values that are positive or 0. So it's not going to be taking the negative, it's going to be taking the positive. So this is the kind of graph you're going to have. Okay, this obviously becomes like the square root function. Okay, but what do we do with this here? Right, so at this point, I was trying to say, obviously, I mean, you can use any of the present. You can make X the subject, Y the subject, doesn't matter, but you need to be systematic in the way you substitute your things here. Okay, let's continue. So this is the limit. Now, here we made Y the subject. Okay, so if we made Y the subject, you would have, therefore, if you substitute, no matter you substitute here to make sure that everything is clear. Y, wherever there is Y, we put X to 1/2. 2x. Wherever there is Y, you put X to 1/2 divided by X squared plus X to 1/2 squared. So, okay, this is square, please. Because it is 2xy squared, so we square here, and this one is x squared, and then here is y to the 4th power. Okay, this approaches 0 and 0. It approaches 0 and 0. Okay, let's just continue. This is the limit that approaches 0 and 0. Okay, then continue, please. So it approaches 0 and 0. And then, now the first one says x approaches 0. The second coordinate says that x to the 1/2 approaches 0. But if x to the 1/2 approaches 0, is the same as saying x to the 1/2 approaches 0, means that this can only happen when x itself approaches 0. Okay, so that this is going to be x approaches 0. Okay, now if you come here, this one is 2x times. If you square the square root, it becomes just x, which is x squared plus, if you square this one, is x. Okay, good. Here, the top, the numerator of the expression just got 2x squared at the top. Okay, we can just factor out the denominator, x plus 1, like so. Okay, this is good. And we can attempt to simplify this. Let's do it in green color. X is going to cancel one factor of x, giving us 1. This becomes the limit as x tends to 0 of 2x. Okay, because we left with 1x, 2x over x plus 1. I made a mistake. Made a mistake here. Okay, this one is to the 4th power, so this must be 4. Okay, this is x squared, but this is to the 4th power, so this must be 4. Wondering why it's the same 0, because I'm expecting this answer to be different from the previous one. The previous limit you got to be 0, so because it does not exist, you must choose a curve that is going to work. Some curves are going to give the same answer, so there's no point of writing a curve that is going to give the limit 0, provided the limit 0 is the only one under any conditions. Okay, so I was then saying, okay, this one is x to the 4th power. So x to the 4th power, so it's like you take half of 4, you get 2. Okay, this is good. Now let's come here. Bottom part. Bottom part. So in the denominator, you're then going to have 2x squared. Okay, this is good now, because we have 2x squared over 2x squared, and 2x squared is not 0. So we're looking for a limit that's going to be different. And therefore, this is a 1, and this is 1. Okay? So let me make sure that the limit is not written in ambiguous manner. Somebody's going to watch, because see, I'm recording this video. You're going to have access to these. I'm going to send you the link. So hence, we have the limit as x and y approaches 0 and 0 along curve D of f that, and this limit is 1. Okay, okay, good. So we got one limit was 0. The limit was 0 along curve C, but the limit along curve D became 1, and we then say thus the limit of f, x, and y along 0 and 0, along curve C is not equal to, thus the limit is not equal to the limit as x and y. Okay, thus this limit is not equal to that. Therefore, the limit, according to this, the limit as x and y okay, yeah, it seems these limits are along, these limits are, are different from each other. Right, therefore this limit of f, x, and y is this approach 0. Okay, so this limit here, because that was the question. So writing exactly like this, so this limit here, it does not exist. Does not exist. Well, this limit does not exist because the curves C and D were arbitrarily chosen, were arbitrary curves. So this limit here does not exist. This limit here does not exist. We continue. Right, so this limit does not exist. Since can just bring some justification, since the curves C and D were arbitrarily chosen curves. Arbitrarily chosen curves. Okay, just something that we note here. Arbitrarily chosen curves. Okay, we continue. We continue. All right, so we look at the next question. So because it said show that this limit does not exist by considering limits along relevant curves, and we've just done that. So we just chose two curves that, so it's very important to just choose one curve, normally y equals x, if it's gonna work, and then another relevant curve that is gonna produce a different limit. Okay, but if all relevant curves, like all relevant curves, give the same answer, then we use epsilon delta like we've done before. In one question, we used epsilon delta to prove the result. Okay, so sections 4.4 and 4.7 concern the R2 to R function f given by the following. Right, so in this question now, I want us to spend some time and solve this question in the best way possible, but try to analyze every part of it. Okay, right. So if this is the given question, write down the largest possible domain, d subscript f of the function f. And then what is the largest possible domain? Right, so looking at part A, the largest possible domain of this, it's going to be the following. It's going to be the following. Okay, there are a couple of things that we can see. We're able to see that this function here is the denominator x plus y, so we want the domain, so we must take care of that part. So the domain of the function f is going to contain x and y in R2 such that X and Y in R2 is such that Y is different from minus X. Okay, because Y cannot be minus X. If ever Y is minus X, then we're going to have division by 0 here. Okay, so we're discussing continuous functions simultaneously in this context. Union. Sorry, because this one is a piecewise function, we have taken care of this part. We have taken care of that part. But there's also union. The union is the examiner is adjoining, because 0 and 0 here would mean like if X and Y are both 0, then you have 0 plus 0, which is 0. Division by 0 is undefined. So, but the examiner is like, if ever there is division by 0, then the limit, then the function is 0. So we're going to include those and we're going to join those. So union 0 and 0 together with 1 minus 1. 1 minus 1. 1 minus 1. Okay, yeah. This is what we have. This is so. What is the domain? But the largest possible domain. So we take the domain of f, d subscript f. It contains all the ordered pairs of x and y, because this is a function of two variables. And this is an element of R2 such that y is not equal to minus x. Union, right? Union. We are joining these two. We are joining these two, the 0 and 0 and 1 minus 1. Because if you put x1 and y minus 1 here, x1, y minus 1 here, you're going to have 1 minus 1, which is a big note, and which is division by 0. So the examiner was able to, the person who created this question was able to realize that, okay, if we allow, there are two cases when at least, but they're much more than these. They're much more than these. Because even if you take 2 minus 2, like 2 minus 2 is still 0, so this thing is going to be undefined. So there are many obvious cases where this domain itself would be such that we need to remove a lot of this, but we're removing a lot of them by saying, hey, any y that such that y is not equal to minus x. Y is not equal to minus x. Why are we saying this? Okay, we took this denominator, x plus y, and we want it not to be equal to 0, because we don't want division by 0. So it must not be 0 for us not to divide by 0. Therefore, which means y is not minus x. 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 Okay, so we've taken care of that part, y not equal to minus x, but yeah, the examiner says, hang on, we want to include only these two on top of these. We know that the function is undefined, but include 0, 0, union, but include 1 minus 1. So the others, like 2 minus 2, you might take out, but yeah, these ones, please just include them. So this is the largest possible domain, and we're done with part A. Next question. The next question is part B, and in part B, we're back to the limits. Okay, but now these are limits involving what you call a piecewise function. Right, so these are limits involving a piecewise function. Piecewise function. Right, so determine the limit of this. Determine the limit of these. Okay. Yeah. Okay, now determine the limit as x and y approach 0. Okay, so because now x and y, the point x and y equals 0 and 0 here, we're going to use the top part, because the limit is when we are not at the point, but we are approaching the point. So we cannot use this part. We're going to use the top part, meaning that to find this limit, we're going to evaluate the limit of fx and y, which is 0 and 0. And then this is x and y. Okay, 0 and 0. So we're going to take this limit right now. Okay, the f function, obviously when x and y approach 0, so we're going to take the top part. This one, because x and y are equal 0, so we're going to ignore the bottom part and take the top part of the piecewise function. So that you have this which approaches 0 and 0. And then there's x plus y divided by x plus y. And this is therefore x minus y. And therefore now, okay, anyway, why do we even factorize the top? The difference of two squares here from grade 10, we recall that x squared minus y squared, obviously very basic concept, is x minus y, open bracket, x plus y. And this here is our grade 10 study on what we call the difference of two squares. Difference of two squares. Difference of two squares. So we get this one. And if you substitute the x and the y here, you'd have 0 minus 0, and it's a big 0. Okay, so, and obviously, I mean, the examiner asked us, so we then say hence. Hence, with the limit as x and y tend to 0, and this is 0. And this limit equals 0. Okay, but the answer has two limits, so we're also going to do the other limit. This one here, when x and y approach 1 and minus 1. So now if we're going to do the limit, x and y approach 1 and minus 1. X and y approach 1 and minus 1. So you therefore have that which is 1 minus 1. And this f function, okay, also for 1 and minus 1, we can't use the bottom part where the function is 0. We're going to use the top part because the limit is when we're approaching the points, but we're not actually at the points, because here we're at the points when x equals this, so we're going to use the top part. This one here, okay, of the piecewise function. All right, and just 3 marks, very basic. So we have the limit as x and y together approach 1 minus 1, and this is x minus y, x plus y together with x plus y. So this is the limit. And this is x minus y. If you substitute here now, the x is 1. The y is minus 1, giving us exactly 2. And hence we're able to say the limit of f x and y of x and y approaches 1 minus 1. This limit is 2. This limit is what? This limit is 2. Okay, so we have got the other one, this limit, the other limit, we got 0 there. Here it is. We obtained 0. The limit was found to be 0. And also this side here, the limit was found to be exactly 2. Next point. Right, obviously we've done these up to the A and B parts. Now we're going to look at the other parts. So yeah, we're looking at the next parts. Right, so we're going to look at the part C. Write down the values of the function at these points. So what are the values of the function at these points? Okay, now if you look at 7C, right, so if this is the function, we need to just evaluate the function at 0 and 0. So the function at 0 and 0, what is this function at 0 and 0? Okay, whenever x and y are 0 and 0, the function is 0. So this one is going to be 0. But also the value of the function at the pointer 1 minus 1, whenever x and y are 1 minus 1, then the value of the function is 0. So obviously they said write down the values of the function at 0 and 0, 1 minus 1, and we've written the values. They're both 0. Okay. Next question. The next question is about continuity. We saw continuity at first year when we did calculus B and calculus A, but yeah, we have a chance now to analyze this in relation to a multivariable function, not really limited to the first year notions. Looking at part D, is f continuous at the origin at 0 and 0? Is it continuous or not? Well, I mean, to answer that question, and I would say, okay, I'm going to bring justifications, but yes, it is continuous, and I'm going to bring the justifications. So we're looking at a 7D, so we could say yes. Yes, f. See, this is how, I mean, obviously you need to phrase the answer. So yes, f is continuous. Is continuous at this point, x and y equal to 0 and 0. So it's continuous there. Why? Why? Since the limit. Okay, because now continuity requires that the limit must be equal to the value of the function at the point. So yeah, let's evaluate the limit at this point. So we find the limit at the origin of f, x, and y. What is the limit? We got the limit at 0 and 0. Sorry, the limit of fx and y at 0 and 0 as x and y approach 0. This limit is 0. So, and this limit is 0. We checked that one. But what is the value of the function at 0, 0? The value of the function at 0, 0 is also 0. So the limit is 0, but also the value of the function at the 0 and 0, at this 0 and 0, the value of the function is 0, the limit is 0. So these are equal to each other. And that is the only condition you need for continuity in terms of limits. But in terms of general arguments, a function is continuous if it has no break. And it's just like this. But once there's a break like that, then it is discontinuous. Okay, it is therefore not continuous there. So yes, since the limit is equal to the value of the function at the point, and then we're done. Okay, that was part D. Let's look at part E right now. Part E is f continuous at a different point. Okay, they're asking about the 0, 0, but yeah, let's look at the next one. At 1 minus 1, is it continuous there? Is it continuous there? Right, we need to, we're going to realize that no, it is not. And we're looking at the 7E right now. And the answer is no. F is not continuous. Is not continuous at xy. Is not continuous at this point. X and y equals 1 minus 1. Why? Why is it not continuous? It is not continuous since the limit, let's evaluate the limit to determine continuity. The limit at the point. So the limit as x and y approach the point at the same time. X and y approach the point. The limit as x and y approach the point. Since the limit of f of x and y as x and y approach the point, okay, what is the value of this limit? We saw it. We got 2. We obtained 2. So this limit of f of x and y as x and y approach y minus 1, this limit is 2. So this limit is 2, but this 2 is not equal to the value of the function at 1 and minus 1, because the value of the function at 1 and minus 1, the value of the function is 0. But 2 is not equal to 0. 2 is not equal to 0. Now, because 2 is not equal to 0, it means that this is not continuous at 1 and minus 1. So obviously the question, is f continuous at x and y equal to 1 minus 1? No, it is not. Why? Because if we get the limit, we got the limit before, we got 2, but the value of the function is 0, and this value of the function is not equal to the limit. So we continue. We continue. We continue.
Yes.
Okay, yeah. We move to F. Right, now looking at F, what is the question? Is F a continuous function? Generally, that is the question. Is it generally continuous, this function? Because it is not continuous at this one, and yet it is continuous at that point. But is it continuous then? Well, obviously it is not, because if it is continuous, it must be continuous at every point. So no. Why is this function not continuous? So no, f is. So this would be the answer. So we would say no, f is not a continuous function. It is not a continuous function. Why is it not a continuous function? It is not a continuous function since f, we know one point where it is not continuous. Since f is not continuous, at, there's an arbitrary point, okay? There's a point we chose, but quite a specific point. So it's not continuous at x and y equals 1 minus 1. So it is not continuous at 1 and minus 1. Okay, we saw that, because the limit is not equal to the value of the function at that point. So it is not continuous. So f is not continuous, is not a continuous function in general, because or since f is not continuous at this specific point. Yeah, it is continuous at other points, like we saw that it's continuous at the origin, but it's not continuous at 1 and minus 1. So yeah, we're good. And we move forward to the next question. Right, move forward to the next question. Right, the next question is question 8. In question 8, we want to find more derivatives and the rates of increase, but also the gradients of the function. In terms of the gradient, like this one, the grad bar f. This means the slope of the function in multivariable calculus. Let's find the gradient of this function here. Right. So if you look at part A, this is the function, and we want to find the gradient. Now, to find let f be an R2 to R function. So in other words, it moves from R2 to R. The output is a real number, whereas the input is a set of ordered pairs, is defined by this. Determine the gradient of f of 3 minus 2 by using the rules of differentiation for R to R functions. Read, remark that, never mind that, sir. Right. Took the questions from literature. So we're looking at 8a. The function f is x and y, which is 2x squared, 2xy minus 3. So we want to find the gradient of the function f. By definition, the gradient of the function f is nothing other than, in terms of our notation, it can actually be seen as the derivative of the function like this. So we're going to find the partial derivative of f with respect to x and the partial with respect to y. In the spirit of this course, we can say it is d1f and d2f. So in 2615, when we use the d subscript 1 notation, we mean that it is a partial derivative with respect to x and the partial derivative with respect to y. So we are actually spoiled for choice there. We can use either any of these notations. But if you use f subscript x, it means it's the partial derivative. Obviously, what we mean by that is partial derivative of f with respect to x, contrary to dy dx. So it's the band d partial differential. Okay, so in business, and let's just do this. So we come and then say we're interested in the gradient of the function. But first, obviously, they asked us at 3 and minus 2, but we're going to do first the derivative and then substitute the values of x and y. Okay, so what is the derivative of this function here with respect to x? So 2x with respect to x gives us exactly 4x. Okay, now the 2xy with respect to x, the derivative of the x is 1, and that gives us 2y. The derivative of minus 3 is a big 0. The derivative with respect to y, this one, the 2x squared with respect to y, it's 0. This one with respect to y, just differentiate the y, whose derivative is 1, leaving us with the 2x. And the derivative of the minus 3 with respect to y is a big 0. Moving forward, we are interested in answering the question. So we want the gradient of the function f at 3 and minus 2. That is at that point. Our x is 3. Our y is minus 2. Our x is 3. Okay. Right. So yeah, we can continue. What is 4 times 3? 12. Minus 4. 2 by 3 is 6. Giving us 8, 6. Giving us 8 and 6. So that we're able to then say the gradient of f together with 3 and minus 2, this gradient is 8 and 6. This gradient is 8 and 6. This gradient is 8 and 6. Okay. So we got the answer. And by using the rules of differentiation for R to R functions, we remark that, okay, we've got the answer there. The next thing is we do the rate of increase, 8b. Right, I made a lot of space available for us to just appreciate the rate of increase concept. But first things first, because it is the rate of increase at the same point as the former question, 3 and minus 2. So we're going to obviously be where we are very jubilant, because looking at 8b, we're dealing with the same point, meaning, Mr. Examiner, we take note of the fact that we recall the answer we got, so that the gradient at this point is 8 and 6. Is 8 and 6. Okay, there's something we call therefore the unit vector. The unit vector. Okay, because we want to determine the rate of increase in f at the point 3 and minus 2, which is the same one, right, in the direction of the vector 3, 1. Okay, so I'm going to just do this one. So in the direction of that vector. So there's something therefore we call the unit vector. So the unit vector in the direction of 3, 1 is given by okay, there's something called a unit vector, which is E bar. Okay, because it is actually in the direction of the vector 3 and 1. So write 3 and 1, divide by the length of the vector 3 and 1. Okay, so this here is exactly 3 and 1. Okay, need to write 3 and 1, just a sec. Right, so we have 3 and 1 here. We divide by the square roots. 3 squared plus 1 squared. 3 and 1 divided by the square root of 10. 3 over the square root of 10. Okay, so 3 out of the square root of 10. 1 out of the square root of 10. So we have just found a unit vector in the direction of 3, 1. But now there's the theorem I want to mention. By theorem. Right, so by theorem, seven point 7.3, the rate of increase. The rate of increase in F at the point 3 and minus 2 in the direction of 3, 1 is given by the directional derivative. Okay, there's something we call the directional derivative, and let us talk about it. So the directional derivative means that we are speaking about the directional derivative in the direction of the vector 3, 1, and it is the directional derivative of the function at 3 and minus f, the function f at 3 and minus 2, and this is equal to the gradient. The gradient of the function f at 3 and minus 2 dot product the unit vector. We already know the gradient at this point is 8 and 6. And the unit vector is exactly this one here. You can write 3 out of the square root of 10, 1 out of the square root of 10. So multiply dot product, 8 by 3, 24 out of the square root of 10, 6 by 1, 6 out of the square root of 10. And now if you add 24, denominators are the same. Denominators are the same, so you can add 24 plus 6, getting a 30. 30 out of the square root of 10. In mathematics, we're not advised to leave answers with a set denominator. So we must always make sure that our denominators are rational numbers. So we rationalize. And if we rationalize, we get the following. So the top becomes 30, the square root of 10, you divide by 10. Square root of 10 plus square root of 10 is 10. 10 goes how many times into 30, giving us 3 times the square root of 10. Hence, this means that the directional derivative in direction of E of f of 3 minus 2, this is 3, the square root of 10. 3, the square root of 10. You see, the question was, so this is the answer. Okay, because the question was determine the rate of increase in f at the point 3 and minus 2. So the rate of increase in f is actually this one here in the direction of the vector 3, 1. And we have seen before that using the notion of what we call the directional derivative of the function f in the direction of the unit vector E, we got that it is actually 3, the square root of 10. And therefore, we've been able to get the rate of increase in f at the point 3 and minus 2. Next question. Next question. Next question.
I don't have a question.
Oh, okay, that's fine. Right, I'm moving on. We are moving forward. Thank you so much there for noting that. Okay, right. So we're done with this one. We're done with A and B. Next one. Part C. What is the rate of increase in f at 3 and minus 2 in the direction of the positive y-axis? In the direction of the positive y-axis. Let's look at that one. Let's look at that one. Okay, we're looking at part C. Right, to do part C now, we're looking at 8C. We're going to begin with a narration. We're going to narrate, elaborate, and say the unit. The unit vector. Right, the unit vector in the direction. Right, in the direction of the positive. Direction of the positive y-axis. Direction of the positive y-axis, because it is in the direction of the positive y-axis, is that we must find the unit vector in the direction. So if you have the y-axis and the x-axis, etc., and now we want to just want to demonstrate this one because it's quite geometrical. Okay, now we have this one is the y and this one is the x. Now, if you have here this one, okay, we have those unit vectors like we saw in the 3 dimensions, 1 and 0. On this one is going to be vector E2 and it is 0, 1. Okay, so the positive y-axis is this one. So you're able to see that it is actually there and you have the angle there. So now we use a vector that is in that direction. So in the positive x-axis, it will be the vector 1 and 0, but in the positive y, it will be 0 and 1. With z at that component, it would be 0, 0, 1. So E3 would be 0, 0, 1. Right, so it is the unit vector E with this 0, 1 in the positive y, so that only y is 1 and x is 0. Calculating the next thing. Right, so now calculating as in 8b, we obtain the directional derivative the directional derivative. And this directional derivative is the gradient of the function f evaluated at 3 and minus 2, because it is at 3 and minus 2 still in the direction of the positive. Okay, this is a unit vector, so we did not like divide it by the length, because even if we could divide this one by the length, it would be the same thing. It's a unit vector. So these are unit vectors. They're of length 1. They just have 0 and 1. So we don't do like we did here, because here we divided by the length, because the length of this one, the length is this bottom thing. The length is the square root of 10. And the E must always be a unit vector. So, but obviously we just chose here an easy one, which is the standard unit vector. Okay, in terms of these are called standard unit vectors. Okay. Now we have already calculated the gradient of yes, please. Any question?
If they asked for a direction at a positive x-axis, like would it be the same units that you used for the y-axis? I mean, positive y-axis.
Okay. Yeah, if they could say in the positive x-axis, what will the unit vector be? So in the positive x-axis, we could use this one, 1 and 0.
And negative y-axis.
Okay, negative y-axis, yeah. So it's going to be, that's a good question. So it's going to be 0, but y is going to be a negative. So it's going to vector, it's going to be 0 minus 1, because it's like a point of 1 unit distance from the origin. So it would be 0 minus 1. And then you can come here, negative x-axis, what would it be? X would just be negative in that. Okay, so just introduce some negatives there. Okay, so that is what.
Okay, thank you.
Yeah, that's what you can say. And there's more to these than obviously. There's more to these than what one can say. Okay, yeah, I don't want to complicate things, but yeah, we can express this in terms of trigonometric functions, because you see, I was saying here, you can look at the arguments here, and now this is pi over 2, so you can look at the angles that these are made, and therefore be in a position to say that these can be seen as points or on a unit circle. These things go back to r cosine t, y sine t. Okay, r, y cos r sine t. Okay, I know very well that these would be going back to the things we spoke about, but yeah, because in general, you can express them like this, because some can be a bit tricky if the point is like an intermediate point. But I would imagine, therefore, that all these things, the units are here are associated with this. Obviously, now dealing with a unit circle, meaning that the radius is already 1, so you just have this one here, and take the angles that are appropriate. For example, if you take these things here and you want to find the points here, so yeah, like here, this one is going to be pi over 2. So if the angle is pi over 2, because this is pi over 2 radians, 90 degrees at the top, so you could put pi over 2 there, pi over 2. So you can get all these. So with these, then you can always be in a position to get the correct answer. I want to give an example with the negative x-axis. What is the angle here for a straight line? I just said angles on a straight line. They give pi 180 degrees. Okay, we use radians in this course. So that we have cosine pi, which would be -1, and then you have the sine of pi, which would be 0, and that is why this one would be such that it would be -1 and 0 for the x-axis, -1 and 0. X is -1 and y is 0, and this would be for the negative x-axis, negative x-axis. Okay, just note that one. Negative x-axis. Negative x-axis. Right, so what is the gradient of this? So the gradient is going to be 8, 6. Right, okay, yeah, we got the gradient before. First question, it was about the gradient. So in part C, then we have 8x, but now this one for the positive y-axis, so we've seen that it's 0, 1. And therefore, we substitute 8 by 0. So 8 by 0 plus, this is called the dot product. So therefore, this one is going to be exactly 6. Hence, the directional derivative of f at 3 minus 2, this is equal to 6. This is equal to 6, like that. So, yeah, what is the rate of increase in f at 3 and minus 2 in the direction of the y-axis? So the rate of increase in f at 3 and minus 2 is 6. Okay, good. Now I want us to find the maximum rate, because now we found the rate of increase in given directions, but what rate is maximum? Because there are too many rates in different directions. Each direction has its own rate, but what is the maximum rate? We explain the maximum rate. So we're looking at particularly 8D. What is the maximum rate? So to explain this one, we want to focus on the narrations and the implications of what we call the corollary. And a corollary is a result that is deduced from a very, very useful theorem. By corollary 7.7.5, the direction. The direction of the maximum. The direction of the maximum rate of increase. The direction of the maximum rate of increase in f. Rate of increase in f at 3 and minus 2 is the vector. Is the vector gradient. Gradient of f evaluated at 3 minus 2. Everything is at 3 minus 2 for this question. Right, and obviously, okay, by corollary 7.7.5, the direction of the maximum rate of increase in f at 3 minus 2 is the vector gradient, which is 8, 6. The unit vector. The unit vector in this direction. Okay. The unit vector in this direction. Right. The unit vector in this direction is right. So the unit vector in this direction is 8,6 divided by this. Okay. That is the unit vector in that direction, and we write it exactly that way. And then let us find this one easily. What is the unit vector? Right. Is divided by the length of this vector is the square root of 8 squared, 6 squared. 8, 6. Okay, 8 squared is 64 plus 36. 8, 6. And this one, 64 plus 36 is the square root of 100. 10. Okay. And therefore, this one here, you can say 8 out of 10. 6 out of 10. Divide, simplify this. If you divide 8, highest common factor in 8 and 10 is 2, giving us a 4 out of 5. Highest common factor is 3 out of 5. Divide by 2, get 3 out of 5. Hence, do it in green color. Hence, at this point, we proceed to find whatever is needed. The maximum rate of increase. So it means, therefore, the maximum rate of increase okay. Okay. Hence, the maximum rate of increase. Hence, the maximum rate of increase, okay, in F, in F, it's 3n minus 2 is the gradient. It is actually the gradient of f at 3 minus 2 together with this unit vector 8, 6 divided by the length of 8 and 6. Which is eight and 6 divided by the length of 8 and 6. And this is equal to the following equals exactly the following. Okay, if you dot two vectors that are the same, it is the same as this one here. Okay, so you find the dot product of two vectors that are the same, 8, 6, 8, 6, 8, 6. Okay, so you're dividing the length squared by the length. It is 8, 6. X squared and 6 squared, which is 64 plus 36. 64 plus 36 is 100. And the square root of 100 is 10. And therefore, we have solved this question. And the question was determine the maximum rate of increase in F at 3n minus 2, the maximum. How is this? Because my corollary 7.7, yes, please.
Why couldn't we just calculate the gradient of 3 and -2 without doing the upper part, like the red part?
Okay. Why did you not just calculate the gradient like here? I'm wondering where, okay, because obviously,
like
anyway,
if you would just calculate the gradient of
f at 3 and minus 2.
Yes, you would get 10. Like,
Okay,
yeah.
but we did that. Okay, we did that one. We did the gradient of that one in the first part. What was the gradient of 3 and minus 2? We got the gradient to be this one. Yes?
Oh,
8
yes,
and 6.
yes.
Okay. Yeah, because you see, the way we calculate the gradient here, the gradient of a multivariable function has two components. It has like fx, fy. It could have fz, but just that this one just two variables. Okay, so we did that gradient and we got the gradient of the f3 minus 2. We got it to be 8 and 6. And then multiplied by the magnitude of this. Okay, there's something I want to bring to just context here, because this was like 2 marks. But determine the maximum rate of increase. It actually has implications about the actual angle between this vector and the associated unit vector. Okay, because we're taking the dot product of the vector 8, 6 to find the maximum rate of increase. How is this the maximum? And that is, I'm trying to emphasize the maximality part. So it's 8, 6, like this. Okay. These two vectors, what would the angle be between these two vectors? See, that's the question I'm asking. Because it's about, this is the notion of the associated products, dot products. And the vector 8, 6, you can sketch it where, because this is vector x and y, okay? X and y. And then if x is 8, you put it here, then y is 6, you put it there, and therefore this is the vector. But now if you then divide this vector by a number that's larger, so you're going to be getting a fraction of it. Okay, getting a fraction of this vector puts you like here. Okay, and if it puts you like there, it takes you to a point where, that's fine, it takes you to a point where you have a shorter vector than that one, but these vectors are parallel to each other, so the angle between them is 0 degrees. So yes, please. Or 0 radians. Yeah.
I
Okay.
think my question come from,
Yes.
like, if, I mean, the meaning of a gradient, isn't it like a rate of increase?
Yes, yes, yes. It's the rate of change. The gradient, you can view that as the rate of change. Yeah. Yes, and hence the rate of increase. Yes. To say is the gradient alone, not the rate of increase. Well,
Yes, yes.
okay, right. So because the gradient is rate, okay, because from school, when we do gradient, okay, we're using different notations now, and obviously we're using the derivatives and calculus, but when we're in school, most of the times I even deal with school kids, it's delta y, delta x, which is like change in y, change in x. So in physics, we could say change in velocity, change in time in case of the velocity versus time graphs. So in this case, therefore, it's a rate, because rate would mean sort of divide by time. Okay, so yeah, but I mean, this is, we're on point, because if you say the maximum rate, it would just be the gradient, but we dot it with a unit vector in the same direction. So it's like we are dotting, we're finding the dot product of the gradient in itself. But yeah, just making this one a unit vector, because it's 8686 making a unit vector. So on point, because otherwise the gradient alone would not be a maximum rate of increase, because it's going to be, what is the gradient alone? The gradient of 3 minus 2 is going to be like 8 and 6. It's going to be exactly 8 and 6. And if it is 8 and 6, then you can see, it is not doing the job. It's not doing the job. Why? Because the maximum rate of increase must be a number, and the gradient is a vector, 8 and 6. Is an ordered pair, 8 and 6. So we want to know the maximum rate of increase. So the maximum rate of increase has to be a number, but this one is giving us 8 and 6. And it's something else. It is surely something else. Okay, I'm sure that it's going to be much clearer as we move along. Right, so it's going to be much clearer as we move along. Right. We have the following. Next question. Okay, it's going much clearer as we move along, yeah, but this is how it should be done. Question 9 is about compositions of functions and very, very good things. Right, in sections 1.3 and 7.6, for instance, let f be an R3 to R function. So it moves from 1 to 3 components to just one number that whose square root we're taking, defined by this, and let R bar, bottom bar, be the R to R3 function defined by this. So this one is from the real numbers to order triples. Determine the composite function f, the composition of f and the vector R. Let us find the composite function. Find the composite function. So we do that one step by step. And we have made a lot of space available for ourselves. How do we find the composition of two functions? Okay, now two things. First things first, the function f. It is actually the square root of this one here and then you have R of t. So which means, therefore, you have FR which is f of R of t. So we can, because we need to determine the composite function of f and R and vector R. So this is what we do. This is exactly what we do. And then now we have f. What is vector R? Is this one? T ln t. Vector R is t ln t. So we substitute the vector R there, t ln t. And then we use the definition of the function f, and f of an order triple is going to square the first component x, square the second component, multiply by z, square root everything. So that's what we're going to do. We're going to square root everything. We square the first component, squaring the second component, multiplied by ln t. And this is 2t squared ln t. And hence, we're able to see, therefore, that the composite function can be seen as, like that, can be seen as the square root 2t squared ln t. 2t squared ln t. Two t squared ln t. Okay, so yeah, we're to do the composite function, so we've just done that forward mark. Next question. Right, next question is part B, and in part B, we are saying that write down the domains of, okay, multiple domains, several domains. Let us see now. First, we have the function x, y, z, which is the square root. So I want us to just have the functions put next to each other. So with x squared, y squared, z. And we also have the function r, the vector. So it's a vector function t ln t. And then we have the composition function. And we have seen therefore that this one is 2t squared ln t. 2t squared ln t. So let us find the domain. Let's find the domain of f. Right, so we're going to find first the domain of f. At this point, we can see that the domain of f is going to contain all these other triples x, y, z, which are in R3, such that, okay, because the domain now, the x and the y can be anything because the square root must have positive entities underneath, So the only restriction we're going to have is on z, and we just require that z be greater or equal to 0 because we're dealing with things under the square root. We just can't have the square root of -4 like this because this one is going to be like 2i. And in principle, the square root of -4 becomes a plus or minus 2i, in which case we don't want complex numbers to come up because we are taking square root of negative. So we are dealing with the real numbers here. These are r's and r3s. So we need to make sure that z is greater or equal to 0. Next point. Next point, now want to find this one. So right here, it would be the domain of the R vector function. So this domain is going to contain all t in R, such that, okay, if this is the function, what restriction can we have here? The only problem is these are real numbers, no problem. But here we have the natural log, Ln, natural log of t. The natural log requires that the numbers be positive. So we can only take the natural log. We can only take ln of 2, ln of 3, ln of half, but we can't take ln of a negative number. So we must make sure that t is positive. Remember, we're just taking the domains. Here we have the domain of the composition of these two. This one depends on t, which is a real number. So if t is a real number, then here we're going to take t positive. So because here we have ln t, the natural logs, the domain from school. Okay, at school we don't do the ln, obviously we do the log. If you do the log of x base 3 or anything, the domain is that x itself must be positive. X itself must be a positive number. Okay, for the log to make sense. Otherwise, then using a calculator is non-real and error and whatnot. Those are the kinds of challenges, excuse me, that the calculator will present. Next question. Right, so we're done with those. Right here now we're differentiating the expression. So determine the derivative of this by differentiating the expression, and then we're going to use the chain rule. Let us look at this first part. Okay, so using the differentiating the expression obtained in part A, let us differentiate the expression obtained in part A. What is it? Right, so what expression did you obtain in part A? We obtained in part A that this composition of functions at t was equal to the square root of 2t squared ln t. 2t squared ln t, and then now we're finding the derivative of this, and we are trying to find the derivative, so which means f composition primed of t. What is the square root of this? This is 1/2 because this one can be seen as 2t squared ln t and is raised to 1/2. Just find the derivative using the chain rule here. That we were just differentiating the expression. So bring down 1/2. 2t squared ln t, then subtract 1 and you get -1/2. Then you differentiate the inside. You're going to differentiate first the 2t squared, getting 4t ln t plus 2t squared. The derivative of the ln t is 1/t. Okay, so that is what we get exactly, and therefore this is the answer. It remains to just simplify this. So, which means that it is 1 over 2, the square root of 2t squared ln t. 4t ln t plus 2t. Okay. And therefore, the answer to these can also be written as 2 divides 4, giving us 2 ln t plus t. You divide everything by the square root of 2t squared ln t. So this is going to be exactly the answer to that part. It's going to be exactly the answer to that part. So we've differentiated. But now the next, using the general chain rule, theorem 7.6.1, let us use that one. So using the general chain rule, let us write what the chain rule states. The chain rule states that if you have the following F composition R prime of T is the gradient of F R of T. Okay, give that. So what is the gradient? The gradient of F, Y, Z. So this one it's partial derivative with respect to X, with respect to Y, with respect to Z. Yeah, like that. So now we just need to therefore continue to find the gradient. Okay, because now we need to find the gradient of that one there, right? So finding the gradient. Yeah, the gradient of F, Y and Z, Y and Z. Okay, good. We're just finishing, please. Yeah, I can see the time as well. We just have been cruising, and we're okay. Let's see what we do. Okay, we're going to differentiate this function with respect to x. So this is 1/2 x squared plus y squared z to minus 1/2, and then you find the derivative of the inside, which is 2x z. Okay, check that part. And then we also have 1/2 of x squared plus y squared, and then you have z. And then the derivative is going to be 2yz. And then now you differentiate the last part, and the rate of the last part, fz, with respect to z, is 1/2 of x squared, y squared, z to the minus 1/2, and the derivative of the inside is going to be x squared plus y squared, because the derivative of the z becomes a 1. Right. Now we can simplify this as follows, and then say that this is the gradient of x, y, z. Okay, if you simplify these things here, what this gives is xz, x squared with y squared, yz. Okay, this is it. Okay, so you're going to have a z. Right, good. So yeah, I can see that Tando is joining us. He's going to have a z. And then here we're going to have, welcome Tando. We're just finishing this discussion, and then we're going to start with z. And then the last one is going to be exactly x squared plus y squared. And then you're going to have x squared plus y squared z. Now, if you simplify these things, you get to this multivariable function. Okay, and therefore, if you then perform substitutions, So we are already able to see, therefore, we have the gradient. Okay, we have the gradient of the function x, y, and z. We're finishing this discussion, Tando. Then we're going to start with high school. And then we have xz divided by, okay, so this one here is x squared plus y squared z. And this one is exactly yz divided by the square root of x squared plus y squared z. Okay, let's see now. The last one, because I'm just remembering this one, please. This one, we simplify this to this. So we continue. We continue. Right, yeah, we are finishing, please. We're concluding at Tando. I can see Tando is here. So this is x squared plus y squared. You divide everything by x squared plus y squared z. Okay. That's what we get. We continue.
Isn't it 2 square root x squared plus x squared close bracket z? I
Okay,
think you're missing a 2.
in this one, right? Okay, you're right. So the last one has a 2. I think you're on point. Let's see. This 2 is going to cancel these. This 2 is going to cancel these. And there's a 2 here. Okay, let me just put the 2 there. In particular, the 2 has to be there. This one. Thanks for noting that. So there's a 2 because the rest of the 2 is cancelled, but the bottom one, the last one. Okay, I hope I did not leave that one out there. So, there's that 2 there, like that. Okay. So, with this, I wanted us to therefore be able to do the gradient of the function. Okay, I need to put the arguments of the other things. Okay, because the t ln t. And then we substitute everything here. Right, if you substitute everything, it's going to be x and z. X is t and z is ln t. So t ln t, you divide everything by the following. So we have t ln t. So it's 2t squared ln t. Okay, this one is yz, x, yz. So it's t ln t divided by, okay, this one is going to be like t squared plus t squared because x and y are both t, and then the z. So yeah, it's going to be 2t squared. Finishing this. It's going to be actually 2t squared ln t. And then this one here is going to be tt, which is 2t squared divided by 2. And then here you have t squared, which is 2t squared ln t. Okay. Now, the chain rule requires us to find the derivative. Requires us to find the derivative. Okay, so we continue. We continue. Okay, let's write this one. R of t, which is t ln t. Let's find the derivative. Okay, and then the derivative of this one, the derivative of the t is 1, and this is 1 out of t. Just take note of that one. So we're good. Right. So, okay, we have these two things now. Let us see how far we are, and we recap on our favorite result. That is fine. So recapping on our favorite results, we shall have the following. So write it down here. So we're going to have the following. So let's use purple color. So now whatever we want is the composition of F using this chain rule primed of T. And this here is going to be exactly this formula. The chain rule in theorem, which is theorem 7.6.1. Okay, it's going to be the gradient. The gradient of F out of T R primed of T. Okay, this is the chain rule the examiner, it comes in the exam. If they say state the chain rule, they mean this one. Okay, and then now we have substituted everything here. And we take the dot product. We take the dot product of this one with this. You can just take the dot product for simplicity, just for the completeness sake. T ln T divided by the square root of 2t squared ln T. T ln T divided by the square root of 2t squared ln T. Two T squared ln T. 2t squared over 2t squared ln T. Dot R primed 1, 1, 1 over T. Okay, I'm going to be very brief. Okay, if you simplify everything here, you dot these things and you add everything up, component-wise multiplication. So it's going to get to T, 2t ln T plus T divided by the square root of 2t squared ln T. The dotting part of this, as we conclude, would be component-wise dotting using the dot product, so that this first times that is T ln T divided by the square root of 2t squared ln T plus T ln T divided by the square root of 2t squared ln T plus T times that. Okay, the T is going to divide, giving us just 2t, and we have 2 divided by 2t squared ln T. Okay, so you multiply everything and you add, it's going to be like this. And this answer is the same as the other one we got. 2t ln T plus T over the square root of that. It's exactly the same as this one. It's exactly the same as this one we got. Okay, when we just differentiate the expression in A straight away. Okay, because these two, there was a 2 there, but the 2 cancelled out and there was no 2 there left. Okay, so we're good. Yeah, this concludes our discussion. Now I'm going to send another link. I'm going to send in another link. Yeah, so thanks a lot for joining us then. It was awesome having this discussion. We started at what time?
12.
Okay, thank you.